on to our next session, Radiation Technologies in Human Health and Environment. To chair the session, I would like to call upon stage Dr. P. Venkatachalam, Professor and Head, Department of Human Genetics, Srihar, Chennai, and Dr. Dinesh Kumar Sinha, Professor, IGMS, Patna. Please join us in welcoming them. I request the chairperson to take over the session and invite the speakers.
Very good afternoon to one and all. So we are going to start the session 5. It is on technologies in human health and environment. So this session is having 3 lectures, which will be shared by myself, that is Dr. Venkatachalam, and my co-chair, Dr. Dinesh Kumar. May I request the first speaker, Dr. Gautam from BRC Mumbai. He is going to talk on food preservation versus food safety, a paradigm shift needed towards the greener alternative. Actually, his specialization is on radiation technology for food security and safety. And for his credit, he is having 142 publications. With a few words, I request Dr. Gautam to start his presentation. Dr. Gautam, please.
To share the work done in this area, and thank you, Chair, for the introduction. Before going in detail, I think, although time is a little short, but I want to give some emphasis on the title, why I have selected this one. Food preservation is very important, that we know, and equally the food safety. But what are the issues coming with these 2 important objectives which need to be fulfilled for food security? Many of you know that initially we have famine, there is a scarcity of the food, and then first phase of green revolution came that led to significant increase the productivity, and that's why food security per se is not that a big issue as on today, but that not tells that future is also going in the same direction. So what are the area where we need to give attention? As per the FAO data, almost 1/3 of the food in the world is wasted. And when we talk about the food losses, this is not only loss to the food per se, there are a lot of indirect losses are there. Like 20% of the loss to the global land, 70% of the loss to the global water bodies, 32% of the worldwide energy consumption, and so on. Food losses is also impacting the environment. Whatever the food losses do happen, that leads to the 8% of the greenhouse gas emissions. So how important this area, and although this topic will be a little different than what you are hearing from last 2 days or more than that, but again radiation is involved as a measure to these issues, how it can solve this. So before going into detail into that, I want to tell you, like, what are the methods, what are the means how one can preserve the food. We are using lot of food preservatives. All have certain benefits, that's why they are being used, but they have also some side effects. Overuse, overconsumption of food additives can also lead to the different disease states and so on, and that's why we can see the change in lifestyle, change in food habit has lot of impact on the human health as on today. Many times using this preservative or disinfectant become a need of the hour, because right panel you can see the wheat samples or even pulses samples. Insect is the one of the major, you can say, spoiler of these commodities. The damage is huge. What to do? And it is not only in India, almost all over the world. What to do? How to address this issue? Even many of you are aware that in India there is an organization called Food Corporation of India. They are authorized or entitled to have the preservation of agri produce. Many are related to the medical professions here. You know what are being used. This I am putting you from the FCI website itself. What they are using? They are using malathion. You know, many of these malathion is a pesticides or insecticides. Even delta methrin is used, and they are bound to use, because if they don't use, we will again the issue of famine will come, food will be not secured. And what is the frequency of being used even for malathion? Just interval of 15 days or 21 days, or delta methrin 90 days. Aluminum phosphides are also used very frequently. And these chemicals leave a residue in the food at a certain level. And now it depends on the regulators how they are stringent in maintaining the MRL level. Many developing countries that is still remain a challenge. And then finally who is going to the sufferer? Sufferer is going to the consumers. If your food is burdened with the pesticide or residue from the pesticides, it is going to affect our health. There is no second thought on that. Issue of ethylene oxide, many of you must have heard, related to our spices by rejection by some of the countries and so on. Even this issue persists in the domestic market too. And only thing depends how stringent you are in the regulation, how stringent you are in the screening of the samples and so on. So this and ethylene oxide produce ethylene chlorohydrin, that is known as carcinogen. Malathion also produces a carcinogenic component and so on. So this is the few examples I am telling you. The many preservatives, or you can say chemicals that are being used for preservation of food has some sort of issue of the residue. That's why even European Union has banned ethylene oxide and so on. Besides, I was just reading one article a few days back published in The Guardian. The report comes from US, but the documentation is quite well established compared to other parts of the world. Many people got sick and many of you died also through the consumption of organic food. Now many of you are very health concerns, we go for the organic food. But organic food you can only take care when you are, as per the growing the production is concerned or farming is concerned. But what about their safety? They are also amenable to all sort of challenges during preservation as the normal food. How you are going to preserve the organic foods? Again, either you have to use some chemical to preserve. Suppose you produce a wheat organically, how will preserve? Insect is not going to discriminate between organic and inorganic way produced wheat. So they are going to equally damage. How are we going to preserve it? So if organic food is also going to be preserved by using the similar means, then it does not remain organic at all. So that's why I am telling. So this there also the question comes. Now coming to the radiation technology, this is one of the physical methods I will tell you that is being used. Oh, I have only 8 minutes, so I have to run fast. So that has been used since long time, more than 6 decades I will tell you. And finally Codex Alimentarius Commission has approved this is one of the safest technology. I will not go in much detail of the technology as such because time does not permit that. But as far as the radiation technology is concerned, this has been approved internationally by almost all international statutory organizations. None of the organizations in the world had disapproved radiation technology, where the fumigants has been even recommended to be banned or phased out in due course of time. Naming few examples like WHO, FAO, IAEA, even our FSSI, USDA, Food Standard, Australia, New Zealand, Codex and so on. And with only 4 sources of radiation, because energy is good enough to serve the purpose, that is not going to induce any radioactivity in the food, and they are amenable for the application in radiation processing, and this is internationally approved. Many of you have like put your bags on the airport and so on. Those who are not familiar with this technology, just you are putting, similarly you are exposing your food as you are at the airport through the X-ray machines. Same way food is exposed to the radiation sources, and then you take it out, what it does? It kills the insects or parasites available in the food, and that's why make your food safe. Besides, also do some sort of, you can say, growth inhibition, like as happened in the case of sprouting, in the case of potato and onion. So that's why the physiologically their growth is retarded, and that's why the shelf life is increased, and so on. This is one technology. I will tell you this is the physical technology that has a multiple application. And one most important point which I want to tell you, this is the cold technology, or you can say the cold pasteurization, because you can pack the product, treat it, and your product is not going to be heated. There is no increase in the temperature. So that is the best part of this technology. Otherwise, most of the food preservation technology are based on the heat and so on, and that affects the like aroma of the compounds and even texture of the compound and so on. That advantage one has with the radiation technology. Government of India has given approval for almost all classes of food, now putting in the 8. I am not going to name 1 or 2 as per the time restrictions, but almost whatever the food you can think, as per the Government of India regulation, that has been approved by the radiation processing of food. This is the list for that, and even for allied products also that has been approved. Not only in India, even US has approved, USDA approved even for spices up to 30 kg grade dose. European Union, they are much more stringent in giving the approvals. Even they have also approved food radiation for the various commodities. I will give you some successful story which BRC has addressed, and that's why the consumer confidence. Like one of the example is onion. India produces huge quantity of onion, and onion growers or farmers are very much suffering, because many times the price fluctuation is there. Even sometimes government also suffers due to onion. That's what I'm telling. So one can preserve onion by radiation technology very, very well. And this example I will show you. If you don't irradiate, it spoils very fast within 3 to 4 months. And if you irradiate and keep in perfect cold storage, one can go up to 7.5 months. What advantage it gives? It gives you advantage having the price stabilization. Neither farmers are bound to sell at throwaway prices, not consumers are going to penalize with the heavy prices. So you have the advantage both, and we have not only not lab scale, we have done a collaborative study with the Department of Consumer Affairs, Government of India, and then this trial we have done with 1200 tons of the quantum of onion. I think one of the largest scale, you can say, R&D study done internationally, where we have taken such a huge quantum of the produce, and we have shown that this produce has been distributed to the farmers. We have upgraded our facility at Lasalgaon to showcase this technology, and after this, even one farmer producer organization, they have stored onion after this successful trial, and they have sold a few days back. Subsequently, we did a Kisan Mela, or farmers, you can say, gathering, and our chairman and director BRC both were present at that time, and we have distributed the onion to the farmers to their, you can say, confidence build up. Similar thing, we have addressed the issue with the potatoes also. Potato, what advantage? Potato is the produce that is maximally given the processing industry. And after radiation, one can keep a temperature of 14 degrees or so that it has the better shelf life up to 8 months, and you are preserving the energy also. Mango is one of the successful story. India is exporting mango from 2007. Many will be surprised to know prior to that for 18 years mango export were banned from India. We are not exporting mangoes. There is the issue of the pest. When we resolved the issue of radiation technology, now mango is being exported to the USA, and now we have started to Australia, Malaysia and South Africa also. Now we have done 2 years back through the sea route also. One important point I want to highlight here, when mango is being irradiated in India, USDA sends its inspector and sees all the facility, and what message giving they have, what level of confidence they have the technology. They want the mangoes to be irradiated in their presence, and then only those mangoes will be exported to USA. That sort of confidence even our regulators and our consumers also need to have in our own technology. So in absence of USDA inspector, mango cannot be irradiated and exported to US and so on. So that is the important part of the regulation that we need to follow, and we need to learn, and we need to implement for the ensuring food security and so on. Many of these food products, they are very, you can say, highly seasonal in nature. If you do processing, you do a lot of value addition. I always ask the people how much you pay for the potato, how much you pay for the potato chips. So when you do the value addition, it helps the growers, it helps the industry, it helps the food industry, and that's why we have developed many products. Those are available on Amazon, and they are being preserved using radiation technology. and being sold, and many times people ask whether irradiated product will be accepted by consumers or not. The link you can copy and go and through see the consumers are very good review for that. So the acceptance is also not issue. Only thing you have to make them very well aware of the thing what it is. Wheat I have shown you. I will give you an example. Suppose you take 1 kg of wheat today, keep in your house, and you can call me after 4 and 5 months what happens to it. It is going to be badly damaged even for the pulses. But what you get in the market, are you going to be similarly spoiled? No. Are you asking question why this is not happening? Because they are heavily fumigated. Heavily fumigated with the insecticides or pesticides, and that we are consuming. Only thing, fumigated product as per our regulation does not have any labeling requirement. We are unaware of that. So that's why. But if you try to see that, you will get your results yourself. So that is the thing. But if you irradiate, one can keep the sample up to more than 1 year in the very good conditions. Besides many other products, now I know how many you know. McDonald's is using irradiated tomato for all their fast food preparation in Mumbai. Almost 800 tons of tomato has been irradiated this year, and which is being used by McDonald's in India. A sprout, I am telling you, sprouts have a lot of anti-nutritional factor. Radiation not only preserves, it has the value addition. It reduces anti-nutritional factor from spices, sprouts, which we have published also in good international journal. And this technology also has been used by many industry, which are taken from the BRC. They are using it. Spices already I have told you. Again, it is heavily burdened with the microbes or pests, where radiation can easily solve the problem. And that's why most of the facility in India today is using this. For place food also, like after radiation, you can keep fish and meat in the chill condition for a month. So otherwise, what people are using formaldehyde, again you know that is producing a carcinogenic compound. So that fish can be preserved for a year, for a month after radiation processing in chill condition. Sir, I will take this. This is one of the important. I will take this one. This is one of the important commodity waste that is being consumed almost worldwide. You can say bread. We take bread in the different forms and different preparations. But what happens after 3 days? You must have seen the best before date. How many days? 3 days, 4 days? What happens to that? Almost 22% of the bread is wasted all over the world. But if you irradiate, one can keep up to 10 or 15 days. How much one can preserve? How much revenue one can save by this? This is the data for the wastage of the bread worldwide. So I will just skip all those things. So DA has taken the lead. We established 2 facilities. Today we have 28 food ration facility operational in India. We have also come out with a new design like low dose irradiated for the fish and electron beam irradiated for the high throughput and so on. Now we are making a new grain irradiated for solving the issue of grain in Lasselgaon. Probably within 1.5 years it should be commissioned. We are going to make, when we made the successful study, Maharashtra Chief Minister asked us, can you treat 10 lakh ton of onion? We want to create onion Mahabank. Then whatever the facility we have, they are not capable to treating that one. So we have a new design which can treat 5,000 tons of onion in one particular day. So that we are going to come through. These are the steps for the setting the facility and so on. Having all this success story, just the concluding slide, Government of India this year, this budget, they have come out with the proposal for supporting financially for setting up 50 multi-product food ration facilities in the country, and that is, they have come out with the expression of interest for that. And many industry has shown, if somebody, you know somebody or some industry is interested, they can contact me, I can try to help them in this regard. But this is going, so after this plant, 50 plants got established, India may have probably in coming 200-300 plants, food ration plant in the country to treat many products. We require even much more than that. With this, thank you very much.
Thank you, Dr. Gautam, for enlightening your so many years of experience on preserving the food without much damages. Is there any questions from the audience? 1 or 2 questions?
I think due to lack of time, the organizer is asked to interact with directly to the speakers in break time. So,
thank you so much, Dr. Gautam. Thank you so much.
So there is a slight change in the next session, and there is a preponement of the next talk. And may I request Dr. B.N. Pandey from BRC Mumbai to deliver the next talk, that is on emerging concepts of cellular communication in radiation biology, from basic biology to tumor control. So Dr. Pandey, please. So Dr. Pandey is radiation and cancer biology section is from, and radiation biology and health sciences division, Bhabha Atomic Research Center, Mumbai. Sir, please.
So, good afternoon to everyone, and just I like to take you maybe some different subject which have been not much discussed in the literature, and I'm going to talk some concepts which are like almost in radiation biology we don't consider it very important, but they are very important especially for most of the radiation biologists sitting in the audience, and especially for radiation oncologists, which is going to be something like what we do in the lab, which I feel that is going to be very useful for changing the concept of radiation oncologist and the radiation therapist in the future. So I'm going to discuss some of the concepts that, like as we know that we sit in the hall and we communicate to each other. Same way as we know that in the tissue also cells communicate to each other. They are not sitting idle. They also like to communicate to each other. And if they don't communicate to each other, it leads to the problem. Just like if you don't talk to your family members, if you don't talk to neighbors, we are not comfortable. Same way here also it happens. So I'll just take you, so before I go to take my talk, I just like to, I'm sitting on the behalf of my colleagues in our research team. So I just like to use one slide to introduce that what we have been doing overall. And I'm going to present a piece of the work out of the various activity we are doing. So basically we are working on the radiation biology research with relevance to cancer radiotherapy, risk assessment and management of thorium and uranium exposure. And these are the few research activity. We are working mainly for major research activity, which I'm just showing such for the larger benefit of our audience. Some of you are interested to interact with us. Like we are working on the high radiation biology, which is one of our major research interests. Another, we are working on the radiobiological effect of uranium, thorium, or other heavy metal radionuclides and their decarburation strategy. And also we are working on the novel radiotherapy strategy in combination with nanoparticles. And also we are working for developing some biomarkers, like some of us speakers we have talked about, that how they can be used for the prediction of cancer radiotherapy and outcome. But I'm going to present a piece of the work out of that, and I'm sitting on the behalf of my colleagues, and some of them are presenting also. And so if you go to this cell level or tissue level, basically if you look for the cells are basically communicating to each other by various means, and they are connected through each other by gap junctions. These are some of the functional channels how the cells interact to each other. And in the normal scenario, you know that they secrete the different factors, and through gap junctions they pass to other cells. But especially for radiation, what happens that if you radiation, in case of radiation, if you one cell irradiated, they basically transmit the signal to the neighboring cells, and these from neighboring cells can come here, and you can see that one radiated cell they can affect, and the other cells which are not radiated, they can also show the similar effect. And this effect is called bystander effect, which already many of you are aware. But not only that, we have also found that the bystander cells also, they try to send the signal to the damaging cells, and that is called rescue signal. That also we have shown in our laboratory. In addition to that, they also communicate to the other cells by secreting the different factors. So I'm not going in detail of these factors. I am coming directly to this topic. So in that scenario, if the cells are communicating, how they are affecting to the in the in vivo situation. So like suppose if lung tissue is radiated, they may be affecting to this either the lung tissue itself, or they may be affecting to the distant places organs. Like it may affect to this liver, it may affect to the brain tumor which is sitting here. And so these are basically, they are very relevant in terms of radiotherapy. And these are the scenario where basically how at the cell level the interaction takes place, very complex phenomenon takes place, and you can see that the cells from cell, they can get secreted, they can come to the blood circulation, and they cause the effect to the distant organs. And these are called abscopal effects. So there are two types of effects. Here it happens. One is that we can say the local effect, where basically cells are communicating to neighboring cells, and also it can cause effect to distant cells. This is called abscopal effect. So now I am going to address three questions in the radiation therapy which we basically encounter, that when the radiated cells are there in the mass, how they communicate to the non-radiated cells in the population. This is one question we are going to address. I'm going to show some of the results. Second question, we are going to show that in the tumor, when we are basically radiating part of the tumor, which many times happens with radiation oncologists, they are not able to treat whole tumor mass. So if you radiate part of the tumor by intentionally or by unintentionally, what happens to the other part of the tumor? What happens to the fate of the other part of the tumor? And third question, we are going to address that if you radiate one tumor in the body, primary tumor, what happens to the other distant tumor, other distant sites of the tumor mass at the different parts of the body? So the first part of the talk, I am just going to show that how radiated, so I am not going to show in vitro data, I am just going directly showing to some of the in vivo work. Most of them are unpublished, some work is published. So to address this question that how irradiated cells can affect the neighboring cells, and that also in the tumor mass, what we did that we have taken cells which are radiated with very high dose of radiation, which is 15 gray, so that we are able to kill the cells. Now what we do, that we mix the cells with the unradiated cells. They are not radiated, and we are mixing together in a test tube. And now after mixing together, now we implant the both cells together here. So what will happen, that if the cells are basically, if the cells are affected here, so just I will go back. Yeah. So ideally, if the radiated cells are affecting the growth of these non-radiated cells, we should get decrease in tumor growth. If they facilitate, then there is going to be increase in tumor growth. If they don't affect, then we should not get any effect. So this is the overall concept. So what we did that, first before going for experiment, we decided that what is dose we should use, that is going to be, we can say non-tumorigenic dose, that is not able to give the tumor mass. And we found that 15 gray dose is sufficient to kill the tumor, and it is not able to, that in vitro condition they are not able to give tumor. Now if you mix the tumor, this is the result. You can see that if you take radiated cells totally, you don't find any tumor to appear. If you take only bystander cells, fresh cells, they are giving good tumor mass. You can see that tumor mass is there. If you mix them together, basically tumor mass is shrinking. There is no tumor mass, or tumor mass is becoming very small. Ideally we have got same number of cells, fresh cells, but they are mixed with radiated cells. Now you can see that this is tumor growth in the mice. You can see that this is the control mice. These are the radiated mice, like here, and you can see that in the mixed cells there is a substantial decrease in the tumor growth. That means if you mix them together in vitro conditions, they are not able to give the tumor that much, it should give it there. That means it has got tumor growth inhibitory effect. And these results also be validated by using some of the imaging experiment, where also we found that this tumor is getting, burden is getting decreased. Later on we have done a lot of studies for looking for what is the mechanism behind it, that, and we found that basically in these conditions you can see that there is a substantial change in the round to spindle cells, anaplasia, pleomorphism, etc. And one of the very unique feature we found that the cells, when they are mixed together, they are showing a very more number of spindle cells than the round cells. And this is one of the typical feature of senescence. So when these mass are there, then they basically causing the senescence phenomena. And you can see that here, one of the feature it is happening that this is the, you can see that a tumor from the control leg, and this is the which here the cells are mixed together with radiated cells. And you can see that compared to the control tumor, these tumors are showing white in color. White means the angiogenesis or blood vasculature is very poor. And this we also validated using histochemistry HNE staining, and you can see that there is a number of blood vasculature goes down. And in addition to that, also we validated these results by using the in vivo imaging system, and you can see that in case of the mixed tumor mass where the tumor was growing down, the angiogenesis is going down, and that was validated by expression of CD31 expression, which is one of the marker of angiogenesis. So basically these results suggest that in case of you mix it, it is not only causing the tumor growth inhibition, also it is causing the lower level of angiogenesis. So now moving to the next part of the part, that I just mentioned that if you radiate part of the tumor, what happens to the overall tumor? That many times we are not able to radiate whole tumor, and you have got all the treatment planning system, everything, that so that we cover whole tumor. But I am going to show the results where maybe radiation oncologist view may change, that we don't have to worry about the covering whole tumor. If we are able to effectively radiate a part of the tumor, even you can control the other part of the tumor. So to address this question, that how to radiate this one, what we did that we have designed a very special model of a cone radiator, what we can be fitted to a tele3 machine. We have got a tele3 machine in our department where we have fitted this machine, and we are radiating only about 30% volume of the tumor. So if the volume of 1 centimeter, we are radiating only 3 millimeter diameter. And what we found that if the 3 millimeter is able to radiate control the tumor of overall tumor, we will able to get the shrinkage of the tumor. And this setup was basically, you can see that this is setup was prepared, where we are putting the mice here with leg, and then we are radiating with this is setup which was fitted in the tele-3D machine, and using this we are able to radiate only part of the tumor, and this is the data. So if you are, this is the control leg, you can see black color. If we are unradiated control, it is showing good tumor size. If you take high dose whole tumor, if you cover, you get very good substantial tumor regression. But where even we are able to radiate only 15% volume of the tumor, not 100%, you are able to get almost 70% tumor regression. That means if you are able to, if you give radiation tumor to even part of the tumor, you can control the tumor. And this we have done by multiple experiments. Now coming to the last part of my, the point question we are going to address, that if you radiate the one tumor in the primary site, many of the radiation oncologists, they are worried that they have to cover brain, they have to cover liver, if it is a metastasis. So if we radiate only part of the tumor, one primary site, can we control the distant tumors? And to address this question, what we did that, we have a device, a experimental model, that is basically we say that non-targeted radiation effects mouse model. So what we do here, that we have got, we grow the mouse in tumor in both legs of the mice. One leg is basically we keep shielded, like we shield whole body, and almost we get 99.9% shielding. And other part of the body basically, this we are not, we are radiating. So one tumor we are radiating, other tumor we are keeping unradiated. They are kept away from the primary site of the tumor. Basically they are away from the field. And you can see that this is the result. So if this is the control tumor, you can see this is the control tumor, this is directly radiated tumor. Here also you can see that if you take this control, compared to control tumor, even the shielded tumor also they show the regression in the tumor size. It is tumor growth control. And what we found that, we also found that these tumors are showing the increased lymphocyte infiltration, like you can see that these are showing more lymphocyte expression. Then also it has got calcium expression, which is one of the marker of immunogenic cell death, and this in this shielded tumor. So what we ask, if it is causing the immunogenic cell death, can if you combine with the immunogenic cell death modulator like CpG-ODN, which is one of the oligonucleotide which induces the tumor immune system of the mice, we found that when you combine with this tumor, there is a significant decrease in the tumor size. So basically, if you combine the immunomodulator with, along with this shielded tumor, we can have more control of the distant tumor. And not only that, this type of treatment, basically they are causing long-lasting effect. Basically, if you take these mice which have got tumor control and if you put fresh tumor cells, they are not able to allow, they are not allowing the tumor to appear. You can see that this is the tumor, fresh tumor, and if you take these mice which are having this already treated, they are not able to make the fresh tumors appear in this system. And this is the also we wanted to verify that what happens to these some of the immunogenic marker like CD8 expression, which is one of the T cell regulator. And we found that compared to, these are the control, these are the ODN basically immunomodulator, and these are the 5 gray, it is not showing good number. But if you take this 5 gray plus ODN, it is showing substantial increase in the level of CD8 expression. And previously also we found that is a higher level of lymphocyte expression, infiltration. So taking together this is that if you take even this is the basically whatever effect we are getting, this is nothing but this is immunomodulatory response of system getting immunomodulated, and it is causing the effect of. So based on these results, I just try to show overall results. I am not going very fine details since lack of time, to just give some of the glimpse of our observations. So basically, if you look for the bystander or non-targeted radiated cells in a population, are not bystanders. See, always believe that we are bystander, means they are not bystander. They have got very active role to play, and they play a role that is based on observation. And if you do partial tumor radiation, you can control the other part of the tumor. But that is again a confidence to be built to the radiation oncologist, and the system should be developed that to treat the patients. And even the shielded tumor also can be used for enhancing the combination of immunogenic agents. So if you combine with some immunomodulators, even you can have more enhanced effect. And these research areas are like, that is why still if you ask for abscopal effect, many of the radiation oncologists or many of the medical field people, they don't believe it. The reason is that we don't have much research, and there is a lot of research needed. We need to have a lot of mechanistic angle to be coming out, and there is a requirement of bedside translation of non-targeted effects of conservative therapy in challenging the task, and that is why basically we need to come together and to work it. So with this, I like to acknowledge the colleagues of BRC, and some of are here, and also this some of the work parts of the first part of the work what I presented, it was done by one of my PhD students, and also I like to acknowledge the collaborators, some of us here, Dr. Nagaraj Ulgol or other people, and Dr. KP Misra, who is my mentor, and also one of Professor Azam, who was my mentor during my postdoc from USA. And this is last slide where since I come from the Bhabha Atomic Research Center and I am one of the faculty of Homi Bhabha National Institute, so just for the younger students, this is about this institute. So thank you very much.
So thank you very much, Dr. Pandey. It was a very nice talk and very interesting one also. So as, although you have said that the practicality of this studies, we have to wait and we have to sit together. So with this, I think if anyone any question, I think we'll take on in the break. Also, one relevant.
Dr. Pandey, congratulations. It's a very nice talk. I just want to know, like, in some of these effect what you have shown, that exosomes also play a very important role. Secretome, basically the tumor secretome.
Yeah.
So, and not only in sensitization of the neighboring cells, it is also demonstrated that some of these secretome can make resistant also to the neighboring cells. So what is your take on this?
So exosomes basically, if you look for the, in fact we are looking for systemic effect in most of the cases, especially for the last part. So systemic effect, exosomes also may be playing a role, but here mainly we focus on cytokine part. So and also immunomodulators, but exosomes part we have not studied. They may be also taking place since we are giving very high dose of radiation. Since what we found that if we give lower dose 2 gray, conventionally what you use, these effects are not prominent. But if you use high dosage like 6 gray, 5 gray, they are prominent. So that is why this we feel that this system is going to work more in case of SBRT, like people like using high dosage. So there it is going to be more effective, and even for the high dosage of charged particle therapy or maybe proton, where we have got massive damage, where basically antigens are coming out and they are getting more expressed for the getting acted by the immune system. But exosomes part we have not studied in our study.
Thank you.
Thank you, Dr. Pandey.
Thank you.
Yes, I think there are only 2 presentations for the session. So on behalf of the organizers, myself, chair and co-chair, thank the presenter for the for completing the session within time for this. Thank you so much.
Thank you very much.
Thank you, Chairperson. Thank you, speakers, for the wonderful insights. And now I would like to request Dr. Pandey sir to come up onto the stage. We'll move on to the next session for poster presentation.
Going to our poster presentation, our first poster presenter is Niyati Dhingra. So please come. And your time for presentation is 3 minutes and 2 minutes for the question session.
I'm here to present the poster entitled Modulation of Combined Radiation and Wound Injury Induced Hematopoietic Suppression and Organ Damage by Trichostatin A. So my current study focuses on the development of countermeasures for combined injuries, which is another aspect of radiological and nuclear accidents where radiation exposure is often coupled with other assaults like skin injuries in forms of burns and wounds. So combined injuries lead to more severe outcomes in terms of hematopoietic suppression, GI damage, all of which can lead to multiple organ damage and failure and ultimately death. So till date we do not have any FDA approved countermeasures for combined injuries. So we hypothesized trichostatin A to be a potential radio mitigator for combined injuries. Trichostatin A is a class 1 and 2 HDAC inhibitor which enhances the acetylation status in the cell, thereby allowing easy access to the repair machinery. Our experimental approach is as follows. Firstly, we generated a dose response curve to determine the LD50/30 value, and TSA efficacy was evaluated at LD50/30. Survival was considered as a primary endpoint and wound healing was considered as a secondary endpoint. For the mechanistic studies, we evaluated the systemic changes and organ toxicity. Our survival showed that wounding decreased the LD50/30 radiation dose from 6.4 to 5 gray. At 5 gray, we observed trichostatin A efficacy in dose-dependent manner with 5 doses providing 83.3% survival. We also observed accelerating wound healing in TSA administered group with up to 99% of wound reduction. We observed ameliorated changes in bone marrow counts, splenocytes and WBC and platelet counts. We observed that trichostatin A also reduced the radiation-induced apoptotic damage in bone marrow. For the organ toxicity, histopathological analysis of spleen, bone marrow, liver and kidney were done, and we observed that trichostatin A maintained the cellularity of the bone marrow and spleens and reduced the vascular damage in liver and kidney. We also observed regulated HDAC activity. So concluding on that, we observed that combined injury animals experience more deteriorated changes. We saw the potential of trichostatin A as a potential radiomitigator in combined injuries. Summarizing all of it, we believe that regulated HDAC expression might be addressing the multifactorial challenges associated with the combined injuries. Thank you.
Thank you, Niyati. One question is allowed.
What are the other endpoint analysis you performed for trichostatin A effect?
Yes, sir. Sir, we have performed like wound healing aspect in depth, which we are not showing here. We have also observed like beyond that, we also observed like in-depth mechanistic studies of bone marrow we have done, which we are not presenting. Like we have studied the expression of BAX and BCL2, which are apoptotic genes, and we are studying the acetylation status also.
Apart from acetylation, what are the other endpoints, molecular endpoints, with regard to trichostatin A and the HDAC or deacetylases?
We'll be studying the inflammation status. NF-kappa B mechanism will also study. So
Okay, that's good.
Thank you, Niyati. Next is Rishabh Kumar.
A very good evening to all of you. Myself Rishabh Kumar, going to present my work on the topic entitled Radiation and Thermal Injuries, a preliminary study of their combined effect on mice to develop a radiation combined burn injury model. So we are trying to simulate the conditions of radiation combined burn injury which happens during the nuclear disaster or nuclear accidents. So what is the combined radiation injury? Already told by one of my colleague Niyati Dhingra. So let's talk about once again any type of physical thermochemical trauma combined with radiation exposure at a dose sufficient to diminish the likelihood of overall survival or functional recovery. Why radiation combined burn injury? Because from the previous data of the nuclear accident like Chernobyl and nuclear war like Hiroshima and Nagasaki, we have observed it was observed that 60% of the victims were injured from radiation combined injury, and this radiation combined injury increases the morbidity and mortality in the synergistic manner. So thus, because of the delayed wound healing and its complex pathophysiology, it complicates the treatment. So previously in 2023, a recent report from the Kiang and Beckley reported that distinct changes occur in different parameters occurs after radiation in response to different injury scenarios. So for each and every injury scenario, there must be a specific, there must be a standardized parameter values so that it can be compared with individual injury as well as used for the efficient treatment of the combined radiation injury. So our objective is to analyze the hematological changes and lymphoid organ cell count changes, and third is to know the pro-inflammatory gene expression changes at various stages of the wound healing. Next is the methodology, where we have used our patented thermal burn devices, which overcome the limitation of contact pressure and thermal contact, and as well as thermal contact. And after that, we have developed a partial thickness burn model with 80 degrees Celsius for 40 seconds. And why partial thickness burn model? Because it is more painful, inherently more painful than other burn injuries because of the exposed nerve endings. So after we have prepared the combined radiation burn injury, we move to know the hematological changes, lymphoid organ cell counts, and protein expression of RCBI through the cell lysate. Now these are the results where we have found that the changes were observed in all the different groups, which are radiation alone, control, burn alone, and radiation plus burn. However, the changes observed in the radiation plus combined burn injury was more pronounced in comparison to the radiation alone injury or burn alone injury. Similarly, in IL-6 and TNF-alpha, we can see an initial rise in the expression of TNF-alpha and IL-6. So at last, we can conclude that the subjects in the radiation plus burn group are more susceptible and at high risk of infection and mortality due to the compromised immune system at the initial stage. And we are going to extending the period of beyond 7 days. We'll have to investigate the long-term effect on immune function and tissue healing. At last, I'd like to acknowledge Director INMAS for providing the laboratory and animal house facility. Thank you so much.
Sorry, no question. Already time is over. Our next is Supriya Mehta.
Good afternoon, everyone. Heavy ion radiation biology is a specialized field of study that explores the biological effects of heavy ion radiation, which is a form of high energy particle radiation. It consists of atomic nuclei like carbon or oxygen that have been stripped of their electrons and accelerated to high speeds. This is particularly relevant in areas like cancer therapy, where carbon ion therapy has emerged as one of the most beneficial radiotherapeutic regimen to treat tumors without affecting healthy tissues. This is because, unlike the conventional low LET X-rays and gamma rays, heavy ion deposit more energy over a shorter and precise distance. Like as you can see in the Bragg peak, heavy ions create dense clusters of DNA damage such as double-strand breaks and complex DNA lesions, which are very unlikely to be repaired by cells, thus proving their higher relative biological effectiveness. There are many ongoing and upcoming research avenues at Inter-University Accelerator Center. Apart from cancer therapy, space biology is also a major application where we require to understand the mechanisms of damage of high energy particles which are being released from distant stars, which is known as cosmic radiation, as well as from solar flares. Also, long-term exposure to astronauts also needs to be studied in order to produce effective radioprotectants to shield astronauts as well as plant and crops in futuristic projects. We are also looking into natural and plant-based extracts from Ayurvedic knowledge for use in radioprotectants. Coming back to radiotherapy in cancer treatment, radiosensitizers are also being developed as certain target or pathway-specific inhibitors or nanoparticles of high atomic number elements that provide up to 25% increased efficacy. Right now, more than 2,000 promising candidates for radiosensitizers are in clinical trials for various cancer types. For conducting all of these research, Inter-University Accelerator Center provides a 15 UD pelletron accelerator, which is a versatile heavy ion tandem electrostatic type accelerator operational to more than 400 to 500 users since 1991. And one of their dedicated radiation biology beamline provides a diffuse beam of uniform distribution over a circular area of 40 mm diameter. The available beamline for radiation biology experiments at IUAC are of lithium, boron, carbon, and oxygen. And so Aspire is automated sample positioning for irradiation in radiation biology experiments. In short, it's known as Aspire. It's a unique unit provided in the radiation biology beam hall that automatically and remotely places up to 20 samples one by one, and the samples are placed in 35 mm Petri dishes to bombard the biological samples with particle beams in air. This enclosure also ensures sterile conditions to avoid contamination in the sample in order to conduct experiments for heavy ion radiation biology. Thank you.
Over time. Sorry, no question. Next one is Nandalal Yadava.
Very good evening to all of you. The topic for presentation is the role of high dose jet interstitial brachytherapy in head and neck cancer and lower abdominal scarications. The purpose of the study to explore the feasibility and efficacy of interstitial brachytherapy in the recurrent head and neck cancer and lower abdominal scarications. SDR interstitial brachytherapy an effective treatment option for the recurrent head and neck cancer and lower abdominal scar recurrence. And brachytherapy radiation deliver a dose to very localized area to the radiation source, which is away from the healthy tissue. Now coming to the methodology, from October 2023 to August 24, we had taken 2 cases of recurrent head and neck cancer and 1 lower abdominal scar recurrence with the C-walled primary for the SDR-ISBT. Average size of the lesion was 6 cm and all patients were either surgically inhalable or defer from surgery. This figure shows the implant. In all patients, stainless steel brachytherapy needles were inserted freehandly and replaced by the plastic catheters. The average number of the needles were 4 in head and neck cancer and 9 in the lower abdominal scar recurrence patients. An average dose of interstitial brachytherapy was 30 Gray 5 fraction, 6 Gray per fraction BID at least 6 hours apart was delivered. And needles were removed just after treatment and patients were discharged next day of the treatment completion. The results were all the patients are currently under follow-up and performing well. In all cases, more than 70% shrinkage of the tumor volume in first follow-up at 1 month and complete regression of the tumor was observed after 3 months. 2 patients had developed grade 1 skin toxicity, that is patients were head and neck cancer, and 1% of abdominal scar recurrence developed grade 3 skin reaction. So concluded that high dose rate interstitial brachytherapy is minimal invasive, safe and feasible treatment option with minimal complication for the inoperable and recurrent head and neck cancer and lower abdominal scar recurrence. And this figure shows the pre-BT lesion and after 1 and 3 months post-BT lesions. Thank you.
Question? Any question from floor? How many cases you have taken?
Ma'am,
It's a retrospective or prospective?
ma'am, this is prospective cases. ये scar recurrence. First one case is abdominal scar recurrence, which is primary was CA vault.
Okay.
And 2 cases of head and neck. One case of buccal mucosa, carcinoma of buccal mucosa, recurrent, and 1 CA lip.
It's retrospective.
Yes.
Next one is Rahul Kabir.
Can I start, ma'am? So, good evening everyone. I am Rahul Kabir from Sri Ramachandra Institute of Higher Education and Research, Chennai. So, the title of my presentation today is Study to Investigate the X-ray Sensitivity in PC3 and MCF7 cell lines. So, it is very well known that radiation therapy is a highly effective cancer treatment modality that is used in almost half of the cancer cases to treat different types of solid cancers and also the hematological malignancies. But it has also been reported that the patients who underwent radiation therapy for the primary cancer, they have an increased risk of developing therapy-induced second malignancies. So, several mechanisms have been proposed to explain the pathogenesis or the mechanism that are underlying behind the development of therapy-induced second malignancies, and bystander effect is an important one. So, behind this bystander effect, it has been found that radiation sensitivity plays as a significant contributing factor, and this radiation sensitivity is basically the way or the process through which the cells respond to the radiation-induced changes. So, with this knowledge, it has also been found that the radiation sensitivity also varies or differs among different cells or tissues. So, with this knowledge, we hypothesize that the magnitude of the bystander response and the signaling pathways and its effects also varies upon the different cells and tissues. So, after this, what we did is that we exposed the PC3, that is prostate cancer cell line, and MCF7, that is breast cancer cell line, with 2 gray and 4 gray of Linac X-ray. And after irradiation, with the directly exposed cells, we have performed the gamma H2X assay, clonogenic assay, and micronucleus assay. And along with that, we have co-cultured the directly irradiated cells with the unirradiated cells, or we can call it as a bystander cells, using the co-culture methodology. So, after 24 hours of co-culture, I have separated both the cell populations, that is directly irradiated and unirradiated, and performed all the 3 endpoints, that is gamma H2X assay, clonogenic assay, and micronucleus assay, to check for the DNA damage and the survival fraction or the clonogenic ability. So, the overall, after performing the experiments, the overall, if you see the overall result, we have found is that the directly irradiated cells shows the dose dependent increase in the micronucleus frequency as well as gamma H2X foci frequency, and there was a dose dependent reduction in the survival fraction for the directly irradiated cells. So, similar similar kind of results we found for the bystander cells also, where we have it has been shown that the bystander cells have also shown the dose dependent reduction in the survival fraction and dose dependent increase in the gamma H2X foci frequency and micronucleus frequency. So, the overall results, what we have found is that basically this result shows the complex relationship between the direct DNA damage and body's response to the and the direct DNA damage and intracellular stress signal communication in body's response to ionizing radiation. And we have found that the MCF7 cells have shown the higher radiation sensitivity, that is it is more radiation sensitive than the PC3 cells. But the magnitude of bystander effect has been found to be more in the PC3 cell line. So this emphasizes the need to consider both the direct effect and both the direct targeted, and that is the non-targeted or the bystander effect, as well as tissue origin, genetic factors, mutation status and other factors for effective therapeutic outcome while planning the treatment modalities for the treating the cancer by the using radiation therapy.
Time is over, no question. Next is Tanmay Roy.
Participants are requested to upload the PPTs in the laptop here, who have not done it previously.
Good afternoon, everyone. My name is Dr. Tanmay Rai. I am DNB resident of Mahavir Cancer Sansthan and Research Center. My topic is on cervical brachytherapy. I have done a comparative analysis between CT-based volumetric calculations and ICRU point estimation of radiation doses delivered to urinary bladder and rectum during cervical cancer intercavitary radiotherapy. Cervical cancer still remains a major health challenge, especially in low resource settings. Intercavitary radiotherapy is critical, traditionally guided by ICRU point-based dosimetry. This study compares CT-based and point-based dose estimation of bladder and rectum, aiming to improve precision and treatment outcomes. The objective of my study was to compare rectal D2CC with ICRU rectal point, similarly the bladder D2CC with ICRU bladder point dose. We have conducted a prospective observational study on 35 patients. Patients underwent EBRT, chemotherapy and intercavitary brachytherapy. Then we have performed CT-based simulation and contouring of dose evaluation, recorded the D2CC and ICRU reference point doses for bladder and rectum, then analyzed the data using SPSS and paired t-test for comparison. The comparison of bladder point and the bladder D2CC revealed a highly significant difference. Similarly, the rectal point and rectal D2CC also revealed a highly significant difference. Both p-value was less than 0.001. We have also compared these ICRU point doses with other subvolumes like 0.1 cc, 1 cc and D5 cc, of which there is no significant difference between D5 cc of both bladder and rectum with their corresponding ICRU points. Rectal D2CC was compared with subpoints at varying distances from the rectal point, revealing differences in dose distribution across these locations. In summary, the result was the bladder and rectum D2CC exceeded the point-based estimates, and subvolumetric doses 0.1 cc, 1 cc differed significantly from these points, and rectal subpoints revealed notable dose variability across distances. In conclusion, the study highlights the superiority of volumetric CT-based dosimetry over ICRU point-based measurements for bladder and rectal assessments in cervical cancer brachytherapy. D2CC values were more consistent, understanding the need of integrating volumetric parameters into clinical practice. Transitioning to MRI-guided adaptive brachytherapy and advanced imaging is critical for precise planning, particularly in advanced stage cases. Emphasizing the cost-effective innovations can enhance accessibility in resource-limited settings, improving the treatment outcomes and standardizing the protocols for better efficacy and safety. Thank you.
Question? Any question? So in each and every case you have gone through MRI based or CT based?
No, ma'am. We have done CT based only.
CT based only. And you compared with MRI?
No, ma'am.
No? Only CT based?
Yes, ma'am. Yes, ma'am.
Okay. Okay, thank you.
Thank you.
Next is Maria Rose Joseph.
A very good afternoon to all. I am Dr. Maria from Mahavir. My topic is to evaluate the impact of CT and 18 FTG PET-CT fusion over radiotherapy planning in carcinoma esophagus, a prospective pilot study. Introduction: the esophageal cancer is the 11th most common cancer in the world and 5th in India with higher prevalence in male. And although chemoradiation is the main modality, but local recurrence are the major issue due to inadequate target volume definition. Here comes the role of FTG PET-CT because it gives metabolic and anatomic imaging, improving tumor localization. So it is superior to CT and for detecting abnormal lymph nodes and metastasis. Objective was to evaluate the difference between PET-CT and CECT in localization and mapping of extent of tumor and regional lymph node involvement, and to evaluate the change in GTV length and diameter, target volume delineation, and impact on dose to OARs. Materials and methods we have taken 33 patients in histologically confirmed carcinoma esophagus of stages 1 to 3. After the workup and imaging, integrated PET-CT was taken in radiotherapy treatment position, and we compared dose tumor volume, alternate risk dose, and nodal inclusion between modalities. The result was like length of gross tumor volume increased in more than or equal to 10 mm in 30.3% and decreased more than or equal to 10 mm in 27.2%. And according to PET-CT, there was an overall increase in GTV length in 63.6%, and diameter also increased more than or equal to 5 mm in 15.1% and decreased more than 5 mm in 21.2%. In lymph node, new nodes were detected in 45.5% of patients. Organ at risk were increased dose were seen and decreased dose were seen in 30.3%. And overall impact was it influenced treatment planning in 78.8% of patients. And there was no change in 21.2% patients. And conclusion is integration of PET-CT enhances tumor delineation, leading to improved local control and reduces recurrence and minimizing healthy tissue damage. It is strongly recommended for target delineation esophageal cancer. Thank you.
Any question?
No, let's not go without asking any questions. No, so just to ask you, simple. What is the difference, major difference between a CT scan and a PET-CT? Why do you want to do a PET-CT?
Sir, CT scan will give you the anatomical details and PET-CT will give the metabolic information.
PET also has a CT, no? PET also has a CT, so that also gives anatomical information for you.
Sir?
PET also, PET-CT also has a CT.
It combines anatomical details along with the metabolic imaging. So we can identify the organ as well as the increase in the uptake in which organ, and usually the disease area won't be more clear in CT, and also metabolic information.
Fine, okay, understood. Fine, thanks.
Okay, thank you. Thank you. Next is the Omal Sharif.
Good afternoon, everyone. I am Dr. Omal Sharif from Mahavir Cancer Sansthan, and I'll be presenting on stereotactic radiotherapy for para-aortic lymph nodal recurrence, a single case report which was done by me and my co-author, Dr. Icrr. For the introduction part, the management of oligometastatic disease has evolved significantly in recent years, with stereotactic body radiotherapy emerging as a promising treatment modality. The rationale of the study was SBRT delivers highly precise and concentrated doses of radiation to targeted metastatic lesions, offering effective tumor control while minimizing damage to surrounding healthy tissues. The incidence of isolated para-aortic lymph node metastasis after definitive treatment for carcinoma cervix remains reported as 1.7 to 12%. This case emphasizes the use of SBRT with the for the treatment of para-aortic lymph nodal recurrence in a patient with CA cervix. For the case presentation part, a 65-year-old female with FIGO stage 3B carcinoma cervix underwent EBRT 50 gray 25 fractions to the primary and pelvic lymph nodes, along with concurrent cisplatin 50 mg per weekly, followed by ICRT 7 gray upon 3 fractions in 2021. And during the follow-up scan, we noted 3 into 2 centimeter para-aortic lymph node, which was detected in July 2023, and it was confirmed through FNAC as polydifferentiated squamous cell carcinoma. And these are the pre-RT PET images which shows isolated para-aortic nodal recurrence, and the patient underwent SBRT with a total dose of 35 Gray in 5 fractions. And for the gross tumor volume was taken as the node, and which was given 5 mm of margin. And this is the image. And the follow-up scan was done. The CT suggested the complete resolution of the tumor. Coming to the conclusion part, with the successful outcomes in this case supported by existing literature, there is already substantial evidence to suggest the efficacy of SBRT in managing isolated nodal recurrences. Further studies may provide additional insights into optimizing treatment protocols and expanding the applicability of SBRT in the management of CA cervix. Thank you, ma'am.
What is your time period between the previous radiation?
Can't hear you.
Time period between the previous radiation and the recurrence you go for SBRT. Is there any time limit?
Oh, sorry, ma'am, I'm not sure about it.
You have already written this patient underwent external beam radiotherapy and recurrence. What is the time lag between these two?
3 years of gap. Thank you.
Our next speaker is Arvati Sai Krupa. Arvati Sai. Next one is Nandlal. Subham Singh.
Good afternoon, one and all present here. I am presenting the role of microglia and endocannabinoid system in the irradiated mice brain. So what happened in the cranial therapy, in the brain tumor, we actually expose the radiation that leads to the cognitive decline in the patients. So actually we are mimicking that condition in vivo. So basically our hypothesis is we expose to the mice to the radiation that lead to the microglia activation, and followed by the reduced level of the endocannabinoids and that cannabinoid receptors that leads to the chronic inflammation, followed by the neuronal degeneration, and that leads to the cognitive decline. And we performed the methodology, 6-month-old mice we used, 4 mice per group, and the irradiation protocol lead the acute had only exposure to the ionizing radiation, and that is 9 Gray, 1 Gray per minute. And after 12 weeks of the irradiation, we checked for the behavioral and cognitive assessment, and the assessment of neuroinflammation and GLUT transporters, and followed by the endocannabinoid system analysis. That means the level of the endocannabinoids and the cannabinoid receptors. So in the behavioral study, we have done various behavioral tests like NOT and objective in place and the temporal order test and 4 sim test, where we found that the mice having a deficit in the recognition memory, spatial memory, and recency. We also checked that 4 sim test for the depressive behavior, and it was found that mice having irradiated that increases the depressive behavior. And followed by we have checked also the Western blotting and see for the GLUT1 and GLUT3 level of the GLUT1 and GLUT3, where we found that reduction in the GLUT1 and GLUT3 level, and in the IHC result we also found that GLUT3 and GLUT5 levels are decreasing. So in the conclusion, we will confirm the signaling pathways by analyzing the endocannabinoid system with these preliminary studies, and the cannabinoid receptor, how it that microglia activation leading to the reduced level of the endocannabinoids and cannabinoid receptors. Thank you.
Any question? How will you go with behavioral changes in this study?
Can you repeat, ma'am?
How will you go with behavioral changes in this study?
Ma'am, we have done that behavioral studies. Behavioral studies doesn't give the reliable results, so we perform the molecular analysis also.
Okay. So you go with, along with this, that you go with a monitor.
Yes, sir. Yes,
Okay.
ma'am. Thank you.
Thank you. Our next presenter is Raja Well.
Good afternoon, everyone. I am Dr. Rajvel from Mahavir Cancer Center. My topic is a prospective study of the response of neoadjuvant chemotherapy followed by surgery and adjuvant concurrent chemoradiation versus radical concurrent chemoradiation in locally advanced lung cancers. So head and neck cancers is a global health burden, overall 57.5% in India, and in tongue cancer it is around 5%. Up until now, concurrent chemoradiation is the traditional treatment option, but recently the neoadjuvant chemotherapy has emerged to improve the resectability of the tumor. Trial conducted in TMH shows is around 40% response in oral cavity cancers in a technically unresectable tumor. But neoadjuvant chemotherapy followed by surgery with added concurrent chemoradiation has also added toxicities also. So using of newer conformal radiotherapy techniques, and these toxicities can be managed. My aims and objective was to compare the response rates of neoadjuvant chemotherapy followed by surgery and adjuvant concurrent chemoradiation to the definitive CTRT in a locally advanced lung cancers, and also to identify the subset of locally advanced lung cancer patients who are most likely to benefit from neoadjuvant chemotherapy. Secondary endpoints are to evaluate the proportion of patients becoming operable after NACT and to assess the acute toxicities in the patients of both arms. So I selected the patients from Mahavir Cancer Center who is presenting in the OPD. It's a biopsy proven locally advanced commercial carcinoma of the tongue cases. And I used a simple randomization is using 1:1 ratio. And arm A was a neoadjuvant chemotherapy arm. It is a neoadjuvant chemotherapy regimen of docetaxel 75 mg per meter square IV on day 1 and cisplatin 75 mg per meter square IV on day 1 and 2, 5-fluorouracil 750 mg per meter square IV infusion continues from day 1 to day 5. This is given once in 3 weekly for 3 cycles, followed by surgical assessment using MRI and clinical assessment. Then if the patient who will undergone surgery and they had received adjuvant concurrent chemoradiation. And arm B is definitive concurrent chemoradiation. Here cisplatin 40 mg per meter square IV on day 1 given once weekly along with the radiotherapy to the primary site and draining lymph nodes to a dose of 66 to 70 gray for 33 to 35 fraction at a dose rate of 22 gray per fraction 5 days a week for a total of 7 weeks. And total sample size was 72 to 36 in each arm. And after the completion of neoadjuvant chemotherapy, patients were assessed at the end of the 4 weeks. The overall response in neoadjuvant chemotherapy arm, it is around 45%, and in definitive concurrent chemoradiation arm, it is around 63%. In my conclusion is definitive concurrent chemoradiation has shown it's a better response rate compared to NSAT, but with minimal toxicities. Probably because of the poor compliance with the longer treatment duration and with the combined chemotherapy with added toxicity in NACT. So even though there are more acute toxicity in NACT, the patients are well tolerated and this toxicity was managed conservatively. So neoadjuvant chemotherapy with the DCF regimen can be an alternative option for a patient with a young age and good performance status in a borderline resectable tongue cancers. Thank you.
What age group?
Ma'am, it is between 18 to 70 years I took.
18 to, and in all cases you go with concomitant chemo radiation?
Yes, ma'am.
Any question from floor?
Thank you.
The next one is Satyam Sarma.
So, good evening everyone. Myself Satyam Sarma from Icrr, Hajipur. So basically my project is on colorectal cancer. We were solving the major problem like majorly in ancient time people used to take the extracts direct as anti-cancer therapy and taking the plain drug as anti-cancer therapy. So what we sorted out here, we just isolated single molecule from the fruits and plants and we designed nanomedicines so that we can target the colon cancer only, not no any other accumulation at the off target sites. So here we planned CD44 based target mechanism nanoparticles where we designed chitosan chondroitin sulfate complex nanoparticle. We have entrapped the phycetin molecule inside. Then we have coated with Udrajet S100 polymer which have ability to localize the nanoparticles at the colonic sites. So what we did before designing nanoparticle, we had network pharmacology study. We found whether the phycetin molecule having any interconnection between the colorectal cancer pathways or not. So we did various network pharmacology study by using in silico based softwares like Venni 2.0 we have did for the target match, and we were found the molecular pathway and molecular mechanism were associated the phycetin molecule in colorectal cancer. Then we selected the specific target protein which is overexpressed during the colorectal cancers like mTOR, PI3K, AKT signaling pathways, and KEAP1 is a kind of biomarker which is getting altered during the colorectal cancer. We docked with this target protein and we were found the positive result in that. After getting positive result in network pharmacology and docking, we should proceed with the pilot in vitro studies. So in vitro studies we perform MTT assay and we profile the expression of those protein by using immunocytofluorescence method by using KEAP1 and mTOR antibodies. So we secondary antibody we use Lexaflor 488 to confirm the expression of KEAP1 and mTOR in the different treated groups. So we were found designed nanoparticles having the positive results in the protein expressions. After that we design nanoparticles. So we design nanoparticle by using complexation mechanism, chitosan chondroitin sulfate complexation mechanism. So then we coated with the Udrajet S100 and we tested into the cell lines. So in the terms of cell lines we performed migration assay and cell cycle analysis. The result was positive. The nanoparticles were characterized in the terms of TM, SAME and AFM. The size was, average size was 100 nanometers. Then we performed the kinetic study. We found 50,000 nanogram the drug concentration is accumulated at colonic site at the 6 to 8 hours. Then we performed immunohistochemistry studies in colon cancer tissue. So we performed KEAP1 and mTOR expressions in balls. So the result was significant in that. So we can conclude that design nanoparticle would be best to consider as a theragnostic molecule if we conjugate the FITC or rhodamine photofluorescence molecules which have ability to detect in the in vivo imaging systems. So this is the conclusion, and we have published approx 8 to 9 research articles related colon cancer nanomedicine design and development. And also we have granted 2 patents recently in German and South African. So thank you so much.
Thank you, Dr. Satyam. Time is over, so no question.
Thank you.
Otherwise, so good presentation.
Thank you, ma'am.
Our last is Parul Gupta.
Good evening, all of you. On behalf of Parul Gupta, I am going to present. I am the corresponding of this particular work. I am scientist here working under Dr. JK at SS Hospital. Dr. Parul is also the biological scientist of this animal group. So the work is entitled Study of Fertility and Hematobiochemical Alteration in Swiss albino mice exposed to 5G cell phone radiation. This work is little bit interesting. There is no such publication for the effect of 5G radiation on any animal model. That is why we started seeing the morphology and some behavior, and we then decided a preliminary work that was approved in January only by the animal committee, and we have taken 21 mice in 3 groups, and one group was control, other 2 group was given radiation for 45 minutes and 90 minutes respectively for 60 days. We have seen some good results, that the body weight was almost the same, but when we see the group 1, that is the healthy one, that is good health, good weight, but the B and C, 45 minutes and 60 minutes, 90 minutes, the body weight decreased. But the interesting result came when we see the TLC, total leukocyte count, and hemoglobin. The group B, group C mice increased in comparison to the healthy one, but the creatinine level was increased almost 2-fold and 1.5-fold respectively for group C and group B in comparison to the control one. If you see the testis size, it was the same, but if you see the histopathology, there was interstitial lumen increasing when we giving radiation to the mice, particularly the male one. For the over-related data, we get some inconsistency, although it is a preliminary work for 21 mice. That is why we are continuing this work. So this small piece work is presented by Parul Gupta. So I wish this work will later be accumulated with more mice and will publish later. Thank you so much.
Thank you all. Our poster presentation, and congratulations to all. Now I hand over mic.
Thank you, ma'am, for chairing the session, and thank you all the participants. With this, we conclude the poster session and we move on to the oral presentation. I would like to request Professor Dr. George Iliakis to chair the session.
So I think we can get started, right? First speaker.
Morphological impact of a non-ionizing radiation on Drosophila melanogaster using NdR laser. In a world increasingly surrounded by non-ionizing radiation sources from medical devices to everyday electronics, understanding the hidden impact on living organism is essential. This work explores the impact of a regulated NdR laser exposure or non-ionizing radiation sources on the genetic and phenotypic integrity of a Drosophila melanogaster. The findings provide important insight into potential genetic and morphological consequences. The NdR laser is widely used in a various fields
in fields including medicine and research. Its ability to deliver non-ionizing radiation raises a question about potential genotoxicity and cellular damage, making it necessary to evaluate its potential short-term and long-term genotoxic effect using a model organism like Drosophila. Genotoxic study has been designed in a Drosophila with an aim to get an important insight into the potential risk of a laser radiation exposure. The study will help to evaluate the mutagenic and carcinogenic effects of a laser, guide the development of safety standards, and offer a model for understanding the broader environmental and health implications of laser use. A quadruple Q-switch Indiag laser was used in this experiment. Wavelength 1064 nanometer, output energy was 850 millijoule, repetition rate 10 Hz. This study employs a controlled experimental design to expose Drosophila melanogaster to a different doses of Indiag laser. Larva, pupa and adult Drosophila melanogaster was exposed to a different doses for constant period of time, that is 5 minutes. Then the flies were transferred to a respective food bottles for further analysis. Following exposure was assessed for genotoxic effects using a standard assays along with the morphological evaluations to identify any alterations in the model organism. To study this, we first of all carried out the dosimetry. As we see in the graph, as the laser intensity increases, percentage mortality also increases. At 0.1 watt, we can observe the adult fly shows a 10% mortality, whereas in pupa and larva shows 50% and 60% mortality respectively. To study the morphology, we use the SEM technique. This is the controlled fly wing. We observe a damage in a wing structure. This is a 1000x. Same magnified image 1000 at 1000x. We can observe a wing hair-like structure we call as a bristle. These are oriented in the same direction towards the tip of the wing. This is the controlled one. We observe changes in a second diagram. First E1 is the controlled one. Second, at 0.6 watt, we observe the wing hair structure got damaged. We can observe in curly hairs. In a GC 0.7 watt, we observe the direction changes and damage in wing hair. In H 0.8 watt, 0.9 watt and 1 watt, we observe a complete hair loss. To study this, we use the somatic mutation and recombination test. This is the short-term and in vivo test that uses a fruit flies to assess the genotoxicity of a substances. The test uses the wing cell recessive markers MWH and flare transheterozygous. MWH is a multiple wing hair and flare 3 flies. When a genetic alteration occurs in a developing wing disk, it can create clones of a MWH and flare 3 cells. These clones appears as a spots on the adult fly wings. Single flare 3 spots or MWH spots indicates the occurrence of either a point mutation or a chromosomal alteration, and twin spots indicate mitotic recombination. We observe significant single flare spots. This is the treated one and this is the controlled one. To conclude this, the presence of significant single spots in the wing spot assay suggests that the laser radiation has a genotoxic effect, most likely point mutation, chromosomal deletion or a wide scale mutation in somatic cell during wing development. The existence of a big spots indicate that the laser radiation produces genetic damage early in the larval stage, allowing the damaged cell to reproduce, resulting in a visible clones in adult wing structure. These findings emphasize the potential of a laser radiation to induce considerable genetic harm in the developing organism. Thank you.
Thank you very much for the nice presentation. Do we have questions? If not, thank you very much.
Thank you, sir.
Then we move on to the next presentation by Vazumati R.
Good afternoon, everyone. Myself, Vasumati from Radiation Biology and Health Sciences Division from Baba Atomic Research Center is here to present my abstract titled Role of Gap Junctions and Antioxidant Enzymes in Cellular Radiosensitivity of Human Cancer Cells to Alpha Particle Radiation. So in 2022, worldwide, the cancer incidence was 19.9 million and the mortality was around 9 million. In India alone, the numbers were 1.4 million and 0.9 million respectively. Among the major therapies used for cancer treatment, 30 to 40% of the cancers worldwide are being treated by a low-LET radiotherapy. But there are certain major disadvantages in low-LET radiotherapy, like damage to normal tissues, induction of radioresistance, poor radiosensitivity of hypoxic tumor cells. So what is the solution for this problem? So among the many thought solutions, one such solution is usage of high-LET radiotherapy. There are two major modes of high-LET radiotherapy: charged particle beam therapy and targeted alpha therapy. But everything is not rosy even in case of high-LET radiotherapy. There are several clinical challenges which are faced, so it is not being employed to a wider extent. So to overcome these challenges, it is very much important to understand the basics of the radiobiology of the high-LET radiotherapy. So the objective of my work is to study the differential radiosensitivity of various cancer cells to alpha particle radiation and understand the underlying mechanisms. So I have used BARC BioAlpha, which has been designed, developed and fabricated in our department for irradiating the cells with external alpha particle radiation. So I have used cell lines of different lineages like lung, skin, breast and human glioblastoma for the screening. So various assays were carried out. Due to time restriction, I am pertaining myself to clonogenic assay. So we have irradiated the cells with 0.5 gray of alpha particle radiation and we have done the clonogenic assay, and we found that MCF7 cells were found to be more radiosensitive than LN229 cells was found to be the least radiosensitive. So what could be the reason for this differential radiosensitivity? So can it be because of the differences in the number of alpha particle hitting a cell? So we calculated the probability of alpha hitting a cell on a nucleus. We found it is not playing a differential role in the differential radiosensitivity. Then we looked into whether there is a difference in the cell cycle phases which is playing its role. We found no direct correlation between the cell cycle phases at the point of radiation and the radiosensitivity. Then we we came down to only with MCF and LN229 cells due to practical reasons. So we studied the repair kinetics. We found the DNA damage to be more in MCF7 cells than LN229 cells at 30 minutes post-irradiation as indicated by gamma H2X, but the repair kinetics was efficient in LN229 cells than MCF7 cells, as MCF7 cells has residual gamma H2X even at 24 hours. Then we know that connexin 43 and gap junctions are known to play important role in radiosensitivity. So we did a scrape loading dye transfer assay to see how much is the functional gap junctions in both these cell lines. We found LN229 cells to have more functional gap junctions than MCF7 cells. Then being connexin 43 as an important gap junctional protein, we looked for the levels. We found again LN229 cells to have more functional, connexin 43 levels than MCF7 cells. Now, how to deduce whether this gap junction is playing the role? So what we did, we used the gap junction blockers, and we had then further irradiated the cells and determined the radiosensitivity again using different assays. But again, I'm fitting myself only with the clonogenic assay due to the time restrictions. So I have used 3 different gap junctional blockers: lindane, glyceritic acid, and 1-octanol. So what we found, these are the representative images with the combination of gap junction inhibitors. There was almost 1.6-fold reduction in the survival when compared to the only radiation group. Then, slide is not moving. Connexin 43 is also known to regulate redox potential, and also it is known that cancer cells with high levels of basal ROS and low levels of inducible ROS were found to be radioresistant. So we looked for the levels of the basal ROS. We found LN229 was surprisingly having more basal ROS than MCF7 cells, but in the case of inducible ROS, that is after irradiating with 0.5 gray of radiation, we found MCF7 cells had more inducible ROS than LN229 cells. So this shows that there must be some mechanism to scavenge the free radicals, which is playing its role. So we looked for the basal gene expression of the antioxidant enzymes using RT-PCR. We found the genes of antioxidant enzymes like catalase, TRX and GPX to be significantly upregulated in LN229 cells. So in conclusion, decreased radiosensitivity of LN229 cells compared to MCF7 cells may be attributed to efficient DNA repair in LN229 cells, which is associated with increased gap junction or connexin 43 and higher expression levels of antioxidant enzymes. So I would like to thank everyone, especially my friends from BRC who helped me to reach the stage till here throughout this conference. Thank you.
Thank you for this very interesting study. Questions? Okay, then I'll be happy to have on the podium Hinashi Narang Mishra.
Thank you. Very good afternoon to you all. At the outset, I would like to thank the organizers for giving me this opportunity, and I'm glad that Professor George is chairing the session. Now, coming to the talk, can I have a pointer? So, the topic is, fractionated irradiation equips the cells for faster misrepair, and I'm from Bhabha Atomic Research Center. To introduce you, as such, the audience doesn't need an introduction to radiotherapy protocol, but as we know that radiation is given in fractions, multiple fractions, which results in preferential killing of the tumor cells while sparing the normal cells. So we were interested in studying with the multiple irradiation of 2 gray, what happens to the cells? How do they change molecularly and cellularly and phenotypically? So for that, we took the A549 lung carcinoma cells and we irradiated them with a 2 gray fraction and 5 fractions of 2 gray over a period of, let's say, 10 days. So every fraction was given 2 days later, 2 days each with a gap of 2 days. And if you give 10 fractions of 2 grays, you would end up having a 10F A549 cells. And after 10 fractions, we would allow them to recover for 2 weeks so that they are fully capable. And then we would compare them to the parental A549 cells. So these are my fractionatedly irradiated cells, and also we wanted to study what happens if you give radiation 1 dose of challenging dose to both of these. One which has been multiply irradiated over a period of time. So here are my experimental subsets. Please keep them in mind. I'll be using them, mentioning them each of the times. So now initially we studied the survival. Obviously at the outset you would want to study the survival. There was radio resistance only at the 2 gray. So these 10F cells were actually not very radio resistant. We expected them to be. And at higher doses they were not at all radio resistant. However, the basal levels of ROS in 10F cells was pretty much low. And then we also had observed the increased expression of ROS antioxidant enzymes, which I'm not showing here. Then looking at how they grow, what is the cellular phenotype, they were growing very slowly. And they had, I'm sorry, I'm just messing it up. Okay. They were growing slowly, as you can see the confluency graph of 10F cells, and they had a larger struct cells. So far, so good. Then we looked at this is annoying. But as they grow, they also tend to develop the higher EMT expression markers like vimentin, and then migration was also higher. So far, so good. These things have already been shown. But we were still interested what happens, and then we looked at the DNA damage repair kinetics using gamma HTX foci, flow cytometry, and the COMET assay. I am just showing the 30 minutes and 4 hours, and you can see there was a significant decrease in gamma HTX foci in 10F cells, as was also observed in flow cytometry, as is also observed in COMET assay. You can see the significantly reduced tail length in 10F cells. Now, this we can say that this probably indicates an efficient repair, because by 4 hours there is a lesser gamma HTX foci, and I would want you to take home this word with you, the efficient repair, and we'll get back to this. Just to see what happens at the proteomics level, whether there is an upregulation of a repair proteins or something, because we are getting the lower gamma HTX foci, which is an indicator of DNA damage. But with the protein, actually we did not observe any upregulation of DNA repair proteins. Even if we did the David analysis, and we found actually there were a downregulation of certain DNA repair pathways. But what here noteworthy is, if you see The red dots are the down-regulated genes, and the these blue are the up-regulated genes. When you irradiate parental with one dose, you see higher upregulation, which we always see, but this is where the down-regulated. So 10F cells always had higher amount of down-regulated genes. This was a different picture altogether. I'm not concentrating it here. So we'll get back to our DNA repair kinetics. Now when we looked at the chromosomal aberrations in A549 and 10F cells, what we see is 10F, which were giving me lower residual gamma HTX foci at 4 hours, were actually showing me higher dicentrics. So the word efficient repair, which I was using earlier, was probably misrepair. So we also looked at the excess, so there were significantly higher dicentrics were observed in these multiple irradiated cells, and also when we looked at the excess fragments, so whenever you observe a dicentric, you have a concomitant fragment with that. So if you match all those, still there are certain fragments which are left, which was an excess fragments. And this was very interesting that 10F cells actually had a reduced excess fragments, while A549 had, again confirming that there was actually a misrepair happening. So ends are actually joining, but they are misjoining. And then we also did the fish. We painted the chromosome number 1 with red. I'll just tell you about the red. So this is a normal A549, which is a karyotype, 2 normal 1 and 1 derivative. But in certain cells of 10F, you could actually see 3 chromosome 1 derivatives. Because it is a larger chromosome, it is more, this to damage. So chromosome 1 was showing 3 derivatives, only 1 copy. So there's a lot of translocation also happening in addition to dicentrics, which confirm that yes, there is a misrepair happening. And then we further, so basically it was not necessarily efficient, however they were equipping the cells for a faster misrepair. So another thing was to understand the repair pathways. So we looked at 53 BP1 foci for the NHEJ pathway to know which pathway is involved. And interestingly, we observed reduced 53 BP1 foci in 10F cells. This, in addition to chromosomal translocation, would suggest that probably some other pathway, when we looked at the BRCA1 foci, which is when we recruited to the DNA damage breaks, would lead to HR pathway, or I would say resection dependent pathway. As you can see, 10F cells had a higher BRCA recruitment. Now this higher BRCA foci in 10F cells suggested that there is a HR pathway, but not necessarily HR, because we can see there are increased translocations, where we are seeing increased dicentrics. So probably BRCA1 is actually taking the cells to the resection dependent pathway, and the pathway which is left is probably alternative end joining repair pathway, because BRCA1 and 53BP1 compete with each other during these early stages, and higher BRCA and lower 53BP1 suggest the activation of resection dependent pathway. HR is FIDL, not involved in chromosomal aberration. This indirectly suggests activation of other resection dependent pathway, which could be ALT-TJ, which can lead to increased chromosomal translocations. So my summary is fractionated irradiation equips the cells for faster misrepair, probably via alternative end joining pathways. Thank you so much, and sorry for the mess.
Well, thank you very much. I found it very interesting. You are out of time, so we will not ask questions. But we will move now to
Thank you.
Pancha Srinivasan for the next talk.
Very good afternoon to all of you. I'd like to thank the organizers for giving me this opportunity. This talk is going to be completely different from what we've been hearing till now, in the sense that this doesn't have any radiation physics, radiation chemistry, or radiation biology, or tissue reactions, but rather this will focus on the reactions from public, what reactions from public we get to nuclear energy, and how the SRR and other radiation kind of organizations can come into the play a pivotal role in altering this perception. In order to do that, we need to quantify risk of different agents. So this talk is going to be about harmonization of the regulatory approach for personal exposures to ionizing radiation as well as for chemicals.
initially this slide was prepared keeping in mind 8 minutes, but now it has been 3 minutes down, so I'll skip this slide because you know it talks about the artificial and natural radiation sources from cosmic to the current mobile phone radiation and various sources of chemicals which are still present in the environment. In summary, I'd like to tell that radiation has been always there and natural sources of radiation has been there, but in terms of chemicals for industrial applications, over 60,000 chemicals have been devised over the last 150 years and more on the rise. So this is a high time we need to take a regulatory approach to harmonize these two agents. So background for setting this exposure limits for chemical substances, it's based on the no observable effects limits or NOAEL, which is a deterministic in nature basically, whereas for ionizing radiation the approach has been to divide into stochastic and deterministic and set the limits based on the risk perceived from stochastic effects for chronic exposures and deterministic for accidental exposures. The last, if you can see here, the table, this is the, there are three major bodies for radiation, that is UNSCEAR, ICRP and IAEA. Whereas for chemicals, you have several different bodies, ASTDR, ACGIH and different bodies. And for radiation, the limits 5.7% per sievert is the nominal cancer fatal probability coefficient. And for public, it's about 5.7%, and for occupational exposure, it's 4.2%. So you see how this translates into radiation dose limits. The same table is transferred here, and you can see here the whole body dose of 20 millisievert is derived from that risk limit, and 1 millisievert for the public, which we use for licensing of the nuclear and radiation facilities, be it any accelerators or any application facilities. But on the right, you can see the occupational exposure limits which are followed for nuclear, for various chemicals, and there are different limits which are followed for chemicals in the chemical industry. Of late, only about 800 to 1,000 chemicals have been defined in terms of the threshold limit values for occupational exposure, whereas there are still 60,000 chemicals and on the rise. So why do we need to harmonize different types of risks? Because as I told earlier, there is a disproportionate risk perception among the scientific community. There is a disproportionate risk communication to the public about the impacts of radiation and impacts of chemicals. Impacts of radiation, of course, this community is doing an excellent job. But vis-a-vis chemicals, how it compares, this kind of information is very crucial to pass on to the public in order to impact the risk communication and the risk perception by public, in order to make them understand which risks are proportionate to the what was presented. So this is very crucial, keeping in mind the nuclear aspirations of India, country like India, where we project like 1 lakh megawatt, that is 0.1 million megawatt by 2047 and 23,000 megawatt by 2030 as an intermediate step. In order to achieve these goals, we need to cross several regulatory steps. So if we don't break this imbalance at this moment, then the cleaner, carbon-free nuclear energy will still continue to remain a dream for the next 50 years. This is one of the biggest risks which we have perceived, having worked in the nuclear reactors and nuclear industry for the past 30 years. So this shows, right under our nose, we can see that the cancer fatality probability from chemical industries are recorded over by following up of 60,000 workers from different chemical industries for about 30 years. So this summarizes all of that data which we have just compressed into this small graph. The annual mortality percent has been 2.4%, whereas for radiation industry it is 1 in 10 raised to 4. This is just to highlight how disproportionate the risk perception has been. So I'll skip this slide because it was very well explained by George Iliakis in the first lecture. So how we can harmonize? By taking the US EPA slope factors, we convert that to the risk, and then there is the current metrology is inadequate to handle this type of risk, to measure risk, because risk is a unitless quantity. So we formulated the equivalent radiation dose for chemicals by translating the risk unit in terms of equivalent radiation dose unit, because the regulator is very much familiar with the millisievert concept. So this we converted for these different chemicals. We have estimated the risk. So you can see the last but one column, the relative risk of other chemical with respect to radiation. For example, trichloroethylene, it is about 11.48 times, and 1,2-dichloroethene, another, it's about 16 to 17 times higher than that of radiation. So this is still data in front of you, but still you see the disproportionate nature of the risk which we ourselves perceive within the scientific community and what risk we communicate to the public. This has a huge impact on the socio-economic aspects of setting up of different types of industries. Why I have chosen trichloroethene? Because the first two chemicals are already used in even within nuclear industry. We have had opportunity to track the levels over the last 30 years. The same nuclear worker is handling the trichloroethylene as well as the uranium radiation. So we had a chance to handle these two. So in summary, I'd like to call upon agencies like SRR, and this result was published in IRPA in 2006 for certain set of chemicals. But the response has been very lukewarm to slightly better over the last few years. Recently, EPA has acknowledged this work, US EPA has acknowledged this work, but we still have a long way to go, because now we have to digest the epidemiological and toxicological information for more than several thousands of chemicals. We have just demonstrated for one or two chemicals how it can be compared. So in order to put the relative perception of radiation and chemical risks to the public, so I call upon different communities, not just regulators, not just nuclear operators, but it has to start from medical professionals in order to understand and digest this amount of toxicological and epidemiological data into this and translate them into this risk. So this is our acknowledgement, and thank you.
Well, thank you very much for this highly relevant talk. We used up the time, so we won't have questions. And we move to Rohit Sharma for the next presentation.
Okay. I would like to thank organizer for providing me opportunity to present my work, the patient dose preparation and study the therapeutic efficacy of 177 lutetium labeled pertuzumab. To start with, I will quickly go through the brief introduction of HER2 overexpressing cancers. These are human epidermal growth factor receptors having tyrosine kinase activity. It exists in 4 different subtypes, HER1 to HER4. And these forms of cancer are highly aggressive because of these receptors are pro-survival in nature, and like TNBC, these forms of cancer are also very aggressive in nature. So, if you see the current cancer therapy module of such type of cancer, it starts with mastectomy followed by chemotherapy, immunotherapy, radiation therapy, and as well as the combinatorial therapy of all these. In case of radiation therapy, the internal radiation constitute a small molecule based radiopharmaceuticals such as peptide based radiopharmaceuticals, or it could be an antibody based agent, that is radioimmunotherapy. So the basic difference, I will quickly go through the immunotherapeutic. These two monoclonal antibodies, trastuzumab and pertuzumab, which are currently being used for targeting these HER2 receptors. The trastuzumab and pertuzumab both are humanized monoclonal antibodies. It is FDA approved antibodies, and it binds to the subdomain 4 and subdomain 2 respectively of HER2 receptor. However, this therapy have certain limitations like disease recurrence, and it also shows cardiac, hepatic, and gastrointestinal toxicity. So we come to the difference between the radioimmunotherapy and the conventional immunotherapy. In immunotherapy, the basic difference in the cell cytotoxicity or reduction in the tumor volume is mainly because of the immune activation of the patient. While in case of radioimmunotherapy, the cytotoxicity is imparted by the radiation dose from the radionuclide that is deposited in the tumor volume. So for developing such lutetium-based radioimmunotherapeutic agent, we chose 177 lutetium because of its favorable physical characteristics, which matches with the half-life of the antibody pharmacokinetics. And since lutetium is a radiometal, it cannot be covalently conjugated with antibody directly, so we need to choose a chelator. And in our case, we choose DTPA over DOTA because of its high radio leveling yield at ambient temperature, and it shows high in vivo stability because of its cyclohexyl ring. So we conjugated our antibody pertuzumab with BFCA, that is DTPA, and we estimated we estimated the conjugation ratio with Malditov, and we found that in each batch preparation we observed ratio antibody to BFCA ratio of about 2 to 2.5. Post conjugation, we label the immunoconjugate with 177 lutetium, and we perform the HPLC analysis and ITLC for its radiochemical purity and its stability as well. So if you see the radio labeling yield for in each batches, we started with a lower activity and we move up to 160 millicurie, and in each batch formulation we obtained a radio labeling yield up to 80% with a terminal in the highest radioactivity case we obtained 111 millicurie of radiation radio level pertuzumab, whose specific activity was in the range of 0.1 to 0.2 gigabecquerel per nanomoles. So once the radio formulation is ready, the next step was to see its stability profile, because it has to transport it to some clinics. So we observed that the radio formulation was found to be stable at 37 degrees Celsius in cell line even after 7 days of preparations. So once the stability study was performed, the next step is to establish its specificity towards the HER2 receptors, because we have brought some changes into the antibody. So for that we choose the HER2 positive SKOB3, which is a ovarian cancer derived, and SKBR3, which is a breast cancer derived cells, and we also took a negative control MDMP231. And in all batch preparation we found that a significant binding was observed in HER2 positive cells, while the negative cells saw minimal or negligible binding with these radio formulations. After specificity, the next point we study is its affinity and immunoreactivity. And all batch preparation we observe it shows a high affinity ranging from 10 to 20 nanomolar towards the target receptor, that is HER2, while since we are modulating our native form of antibody with BFCA and radio labeling, so we calculated the immunoreactive fraction, and in case of immunoreactive percentage IRF, we observe optimum IRF ranging from 70 to 80% of the 177 lutetium pertuzumab. So once these in vitro parameters were established, now we were interested in studying the targeting efficiency of this formulation. So we developed SKOB3 tumor-bearing mice and SKBR3 tumor-bearing mice, and we observed that there was significant uptake of these radio formulations at 24 and 48 hours, and it shows a significant higher uptake in tumor volume. And the last part is its therapeutic efficacy. So we perform the in vitro and in vivo experiment, and we see a significant reduction in the tumor volume in treated mice as compared to the non-treated mice. So I would like to conclude my presentation by saying that we optimize our protocol for developing lutetium pertuzumab with consistently high radio labeling yield, and it was found to be optimally stable with high specificity and stability and affinity. It also has a potential to target the tumor under in vivo condition, and it shows an excellent therapeutic efficacy. Thank you.
Well, thank you very much. This is a very interesting study. Unfortunately, we're already out of time. So we go to the next presentation by Dipali Patil.
Can you start? Good afternoon. My research topic is predicting mean heart dose in left-sided breast cancer VMAT radiotherapy, a comparative analysis of anatomical predictors and art techniques. Breast cancer is a growing global health issue, with cases projected to reach 3 million annually by 2040 and 2.3 million new diagnosed worldwide in 2020. Left-sided breast cancer radiotherapy, heart is close to the breast tissue, creates a unique challenging in radiotherapy, increase the risk of cardiac toxicity, and the key challenges is need for the heart sparing technique to accurately predicting the heart dose. So many previous literatures has explored various approaches to predicting the heart dose in breast cancer radiotherapy. Anatomical predictor is studies like Brackett et al. 2016 and Tasho et al. In 2020, and anatomical parameters these are using the maximum heart distance and breast volume.
number of sample size in 50. AL-based techniques as Siddiqui, Chow and Kao et al. A deep learning model using the maximum heart distance and heart volume and breast volume. And the Wang et al. Utilize a random forest model to predict the heart dose, and this achieve a root mean square error of 1.23 gray. Crucially, we are building on the landmark work of Darby et al. 2013 relationship between the heart dose and cardiac damage, considering the breast volume and heart volume. Our approach is combining the VMAT technique with machine learning, and this allows to improve the dose conformity and organometric sparing. We are incorporating a wide range of anatomical parameters in VMAT technique to enhance our model accuracy and applicability. Our method aims to address the existing gap in current prediction model in advanced technique. And this diagram shows the VMAT and machine learning approach work together to improve the prediction and treatment planning accuracy. The objective of our research is primary objective, develop a machine learning model to accurately predict heart dose in left-sided breast cancer patient treated with the VMAT plan. And secondary objective is to evaluate the impact of anatomical parameters of different VMAT technique, including 2 partial R, 4 partial R, and 5 partial R on heart dose, and identify significant anatomical predictor to optimize the treatment planning. These are our research plan overview. The retrospectively involved 53 female breast patient, and features anatomical extraction in CT slices the maximum heart distance, identify the midpoint of the PTV along the cranial-caudal axis, and measure the maximum distance from the tangent line to anterior heart surface. Tangent heart volume, calculate the heart volume above the tangent line in the field. Heart volume and PTV volume, compute the volume of the contour, heart and PTV volume. And treatment techniques, there are 3 different techniques, and this table shows the 3 different techniques how to creates the arc, and methodology elastic net regression model to use to predict the heart dose accuracy. And how to develop the elastic net regression. The elastic net regression implementation combines the ridge and lasso regression benefits, and it's particularly effective in situation where the importance of certain predictor variable is unclear. It performs the feature selections, automatically selecting the most important variable and reducing the dimensionality of the data, handle the correlate variability efficiently, and optimize for prediction accuracy. And our data set was split into two 70% in training and 30% in testing data set. Model evaluation assess the model performance using the root mean square error and median absolute error on the test set. And the feature importance, remove the target variable heart mean dose from the feature list and normalize the feature importance value to total 1, and rank features is descending order to identify the most impactful predictors. And coming to the results, on this table shows indicate our 53 patients divided into 3 groups: low median risk group, intermediate risk group, and high risk. Group 1 involving into 12 patients, maximum heart distance including 1.4 to 2.25 centimeter, and group 2 involved in 20 patients, maximum heart distance 2.3 to 3 centimeter, and group 3 is a number of patients involved in 21, maximum heart distance is 3 to 4, and heart volume and tangent heart volume and PT volume. This table also shows the volume increases with the group increases. And coming to the result, the group 3, the VMAT, 5 partial arc VMAT, lowest heart mean dose 5.57, and 4.5 in group 3. And this model performance, 5P partial arc outperform in predictions. Root mean square error is 4.8 and median absolute error is 2.11. Overall accuracy of our elastic net regression model achieving root mean square error between 0.91 or 1.08. And limitations of our study consider the maximum heart distance, tangent heart volume, and PTV. In VMAT technique selection, align the technique choice with patient-specific dosimetric goal. Use predictive model to enhance the planning efficiency. Future research, the larger patient population, wider range of another technique, prospective clinical validations technique, and conclude the research work. Elastic net regression model effectively predict the hard dose, multiple anatomical factors crucial for technique selection, potential for improved treatment planning efficiency, and further validation needed for the clinical implementation. Thank you.
Well, thank you very much indeed for the timely talk. Unfortunately, you're also out of time, so we will defer questions and we will move to Rakesh Shuhan for the next presentation.
Good evening to all. My name is Rakesh Chauhan. I am from BRC. My topic of presentation is estimation of dose uniformity ratio and dose rates for cobalt-60 based grain irradiator. Irradiator is being developed for irradiation of a variety of grains and ball species. Considered low-cost, high-throughput irradiation facility to reduce wastage of grains. The importance of the same is described by Dr. Gautam in afternoon session. The irradiator design is having central source chamber with 12 numbers of cobalt-60 pencils of activity 25 kilocurie each. This is the schematic figure of the irradiator. This is the central part which contains the irradiation chamber having the source pencils, and surrounding that heavy concrete shielding is present. This source chamber is connected with the helical path piercing through the shielding for flowing of grain from top to bottom via gravity. The objective of the present work is to maintain close dose rate outside irradiator shielding within regulatory requirement limits for people's safety, and to ensure uniform observed dose by grains in radiation chamber to maintain same quality. Modeling details. This is the typical irradiation section view at vertical mid-plane. This is the irradiation chamber, and here the source pencils location can be seen. This source chamber is connected with this helical path. The helical path is provided in the shielding for reducing the radiation, for reducing the piercing of the radiation, and this blue one is the high density concrete shielding. This one is the plan view of this the cut section at this center line of this geometry. The methodology of the present work is that irradiator modeling and simulation are carried out using shielding code based on Monte Carlo technique. Cobalt-60 radioisotope is used as gamma source, and it emits 2 gamma of energy 1.13 MeV and 1.33 MeV. The dose rate estimation has been carried out on the outer surface of the shielding and at 1 meter away from the shielding surface. Dose profile, dose uniformity ratio, and dose rate distribution inside source chamber are estimated. This is the summary of estimated dose rates. Here it can be seen that in horizontal direction of this irradiator, the maximum dose rate is 0.4 mR per hour at 1 meter away from surface, and in the vertical direction at the opening of this helical top part is 0.2 mR per hour, and these dose rates are within regulatory limit. Estimation of dose profile. For estimation of dose profile, various detectors are placed in the irradiation chamber, both in both vertical and horizontal lines, and the graphs are plotted along the horizontal and vertical lines. This is the dose rate profile along horizontal lines, which are shown by white color in the irradiation chamber, and this is the dose rate profile along vertical lines, which are shown by black color lines in the irradiation chamber. So conclusion of my work is the maximum dose rate estimated on the surface and at 1 meter away from the surface of grain irradiator in horizontal axial direction are 3.5 mR per hour and 0.5 mR per hour respectively. The maximum dose that estimated on outer top surface of the irradiator is 0.4 mR per hour at the end of helical path, and the maximum DUR in grain irradiator chamber horizontal direction is 1.7 for given source pencil location. Thank you.
Well, thank you very much. We have some time for questions. Are there any questions? If not, well, thank you very much then. And I can move to the stage Giri Daribata. We move on. And Alkashana V. Also, we move further on. And then Suspita Munda. Also. And where I go from here, I'm 11, 12. Okay. Then Pisavi Das.
Good afternoon to all of you present here. I am Vishwajit Das from Vitashu University, West Bengal, India. Now, today I am going to deliver my research work on the transfer of radionuclides from the result of the fertilizers used in cultivation. Actually, plants uptake essential nutritional elements in iron forms from their growing media such as water, air and soil. Though soil is the main reservoir for nutritional contents. For obtaining high yields, fertilizers and common people are nowadays involved to use various types of fertilizers because these fertilizers contain various types of micronutrients and macronutrients. Other than nutrients content in fertilizers, some contaminating elements like radionuclides are also present in the fertilizers. The most observed radionuclides are the uranium-238, thorium-232, and uranium-235 DKCG radionuclides, and also the natural radioisotope of potassium-40. But their activity is low in soils, but their activity can be increased by the result of the utilization of some fertilizers which contains radioactivity. So fertilizers use can enhance the radioactivity in soils and find their way into the foods and water. So it is required to measure the radioactive content in the soils and the cultivation plants. It is also necessary for safeguarding the people. Because radioactivity has immense effect on humans. Other effects are shown here. One of the most important foods that we have daily consumed is the rice. It is the critical foods for intake of radionuclides, and more than 50% of the world's population considers it as a dietary stable food. So consumption of rice is one of the most important pathways of radionuclide transfer to rice consumers. So present study for this present study reports the measured alpha radioactivity values in fertilizers, paddy field soils, paddy plant spars, and also reports the transfer factor of alpha radioactivity in the pathway of soil to plants. This study is to my best knowledge, this study is the first in West Bengal. This study is taken in West Bengal region because India's largest producer of rice crops and contributes over 50% of total countryside production in West Bengal. This is the samples description. Here is given. Here three types of fertilizers chosen. Two organic fertilizers, cow dung and mustard oil cake. One is non-phosphate fertilizers, urea, and other fertilizers is phosphate containing. Non-phosphate fertilizer, urea and urea potash, and other fertilizers is phosphate fertilizers. There is given application rate, soil structure, plant spars, soil sample soils. All the samples are pre-treated according to the given by the International Atomic Energy Agency in its technical report series number 295. This is the for alpha measurement we have used the CR39 solid state nucleotide detectors that is very sensitive to alpha particles radiation. This is the first. This is the exposure. This is the setup for alpha exposure. This is the etching machine for etching the CR39 detectors. Here is a sample pillbox type box. The dimension is given here. This is the CR39 detectors, solid-state neuter detectors for use for detection of the alpha radioactivity. Okay, time is. Okay, this is the method and formula. The result. These are also the results. From this, we have seen that after use of fertilizers, alpha radioactivity is increased. These are given here. As alpha radioactivity is increased after fertilization, so this increment of fertilizers, alpha radioactivity will be transferred to the soils and hence lastly transferred to the plants parts. From this, from our study, we have observed that the most important contributors in the transfer of radionuclides is the phosphate fertilizers, obviously for alpha emitters. These are given the values of the transfer factor and transfer of alpha radioactivity from fertilizers to soils. Time limited accumulation, storing time, radio sensitivity are associated with the transfer of radionuclides and also the accumulation of radionuclides in different parts of the plant. These are conclusions. So from this study, I have suggested that the farmers should be encouraged to use inorganic, non-phosphatic fertilizers along with the organic fertilizers, but they should try to avoid phosphate fertilizers as far as practicable, because fertilizers give more alpha emitters in the soil as well as environments as well as local ecosystem, which lastly harms in our health. So this is my suggestion. Thanks to all.
Well, thank you very much for the presentation. We are out of time, so we will move to the next presentation, which is going to be by Suchi Bagi.
Thanks to all.
Very good evening. I'm Dr. Shuchi Bhagi from INMAS, and I'm going to talk about simplifying the gene expression-based radiation biodosimetry for field use during clinical triage. Whenever we are talking about the radiological or nuclear emergencies that could arise either by the usage of nuclear power plant accidents or dirty bombs, such scenarios have the potential to expose large populations to very harmful ionizing radiations, and thus they require a very efficient medical management response. Biodosimetry has classically been a very important part of the medical management of radiation emergencies, and it has relied on the dicentric chromosomal assay being the gold standard due to its specificity, but it has its own limitations for being time and labor intensive. Thus we require more efficient methods that can identify the exposed samples, more number of samples in a shorter duration of time, mainly for the triage purpose. And if we look at the literature is filled with so many studies concentrating on the gene expression analysis as a very potent high throughput biodosimetry tool, although it also has its own set of limitations. Now to make this assay a more robust for a more reliable usability, what we need to think is, if we are thinking about a radiation accident scenario, and if there is an accident which has taken place at center A in the country, and the samples have to reach to a distantly located biodosimetry lab at point B. So we need to optimize the storage and transportation conditions. We also have to have a very reliable, strong, robust gene expression panel, which is modulated in response to radiation. And we also need to have that optimal time window where we can expect the most gene expression response there. So keeping all these things in mind, we have utilized one approach where if we look at the literature, most of the gene expression studies, they have used the fractionated blood. They either fractionate the PBMCs, they culture it, or they culture the whole blood, or they use the RNA stabilizers like RNA later for preserving the gene expression. Here what we have done is we have used undiluted blood, exposed it ex vivo human blood to low doses of 0.5 gray, moderate dose of 1 to 2 gray, and high dose of 4 gray, and then incubated at 2 different temperatures at 37 and 4 degrees, and looked for its transcriptional response at different time points. Now, one of the most important prerequisite is to have a strong panel of genes which we have taken from the P53 pathway. These are the 19 candidate genes that we have studied in this study. And if we see that there was a blunted expression of almost all the genes except for 1 or 2 insignificant spikes when we incubated the temperature, the genes at 4 degrees, while there was a gradual increase in the expression when we were going from, sorry. Can we move to the earlier slide, please? Yeah. So this expression actually increased, and it was maximum at 24 hours of incubation. And there was, if we can see the individual, how the genes were performing, at the red line graph that you can see, this was the incubation at 37 degrees. The blue one is the incubation at 4 degrees. These are for the 19 genes, and 17 out of the 19 genes responded in that way. And 14 out of these 19 genes had significant to very significant changes, especially at incubation at 37 degrees for 24 hours. And we can then segregate it in different panels depending on how they were responding. They were like more than 10-fold increase in more than like 5 genes, which were like highly responsive gene panels. Then there was a moderately responsive gene panel with the 5 to 10 gray of fold change, and then low responsive with 2 to 5 gray of fold change. So what we have done is we have created a radiation responsive gene signatures panel, optimized the time window, optimized the storage, transport, and post-transit conditions, and also simplified the protocol, because if we are thinking about, in any accident scenario, we may not always have the RNA stabilizers available. So how it is better? Because right now we do not have any reliable rapid biodosimetry methods available. Using this method, we can, segregate, we can actually process more number of samples in a lesser duration of time. It gives a result in less than 2 days, because it doesn't really require the culturing of the blood, which is like required for the performing the dicentric assay, and it can be utilized for the triage. And the blood volume needed is also very less. Just 1 ml of blood is like sufficient for doing this. So this was published in IGRB last year. So as they say, it's all in the genes. Thank you.
Well, thank you very much. That's interesting. Questions? Yeah?
Sir, before you ask the question, let me tell you, I'm really glad that you're asking. Sir is one of our mentors.
Okay, thank you. You identified scan for 19 genes, right?
Yes, sir. Yes, sir.
Of which one you found to be a more sensitive or stabilized for up to 24 hours?
Yes, sir.
Out of 19?
So 14 out of 19 had significant to very significant changes, at least at one of the doses.
No, which gene I'm asking? Also, you mentioned that 5 to 10-fold variation and all you observed it, right?
Sorry, sir?
One of the slide you mentioned, there is a 5 to 10-fold increase in the fold change expression.
Yes, sir.
So which genes?
Sir, if you can see, there was a list that I had given with the...
no, out of 19, which one is most sensitive?
Sir, the most responsive were the FDXR, DDB2, GAPDH, and AEN. They were the most responsive.
Okay, thank you.
Thank you, sir.
One more?
Yes, sir.
I'm very impressed. Could you tell me, so are there any individual difference of the increase, individual difference of the increment of the
individual difference?
Individual difference of the change.
Individual difference of the change?
Of the gene expression level in this.
Individual genes, how they were responding?
No, the individual, personal difference.
From the biological samples that you are talking.
Yeah.
Yes, see, this was the, this is the actually, we have taken the average of the different biological replicates that we have taken. This is not from one sample, this is the average of the biological responses. Thank you, sir.
Well, thank you very much. Okay, we'll make an exception. Come on, Yogi.
Thank you. My question is very specific. Have you considered confounding factors in your studies? Confounding factors means genetic predisposabilities?
Yes, sir. Sir, when we are talking about the genomics-based approaches or the gene expression profiles, it is like they are full of confounding variables. There are variables when we look for the genders, there are variables between the ethnicities, there are variables between, the different time points that we are studying, different doses that we are studying. So whenever we are talking about gene expression as a very potent tool for biodosimetry, that's what we have actually tried to do. We have taken the literature knowledge, because these genes were already identified. We did not identify that. But then we have used them for the practical application on the field. So for doing that, we have actually taken out these at least 2 of the confounding variables that we know that it varies with the temperature, it varies with the time point. So at least when we are envisioning that we have to send a sample to a distantly located lab, because that can be a situation in case of an emergency. So at least we know that the most important, how the usual temperature that a sample is transported is like 4 degrees. So if you send me the temperature at 4 degrees, the entire expression is gone. So that was the thing, that at least these 2 confounding variables we have taken here.
Thank you.
Thank you, sir.
And now we move to Yasvrata Dutta for the next presentation.
Good evening to all. I'm Dr. Ajishrata from INMAS, Delhi, and I will be presenting my work on mitigation of the damaging effect of radiation on the gastrointestinal system using trichostatin A. So as we have already heard a lot that gastrointestine is a highly radiosensitive organ, and it is the second most radiosensitive organ after hematopoietic system, and damage to this organ limits the survival of the exposed individual. And here we can see that any full blown GI ARS can be seen at a dose as high as 10 gray, but some of the symptoms can be evident even at a dose of 6 gray. And depending on the radiation dose, the survival can range from 100 to 100 to 0%, and that also occurs between 5 to 14 days. So that shows that the progression of the damage is very fast, and this is often manifested either in the acute phase, which is primarily due to the damage to the intestinal stem cells that are present in the crypt region, which results in the denudation of the epithelial lining, and because of this we can see early death, that is within 10 to 12 days, and those who are lucky and fortunate to survive this acute effect of radiation, they hold a high possibility to develop the delayed effect of radiation, which highly creates health complication and compromises the quality of life. And at present, we know that we do not have any countermeasure that can prevent or mitigate radiation-induced GI syndrome in human, and the supportive, it is only taken care by the supportive care. So these are the different models which can be used to study the radiation-induced gastrointestinal syndrome, and here we have taken the localized model, and before performing the experiment, we have first designed and fabricated an irradiation platform where we could irradiate 8 mice at a time, and the rest of the body parts were shielded. 95% shielding we could achieve, and we first optimized the radiation dose to study the radiation-induced gastrointestinal syndrome using all the recommended endpoints, and we found that C15 gray is the LD50-10 dose, and then we characterized all the animal for different structural and functional changes, and we found that all these changes can be seen when the animals are locally irradiated to 15 gray radiation. And we were also interested for the delayed effect of radiation. So those mice which survived the acute phase, we monitored them, and we found that this is the 6-month study, and we found that at this dose there was a lot of abnormality in the intestine, like fibrosis development, microadenomas, polyps, and since we were focusing only on the abdominal region, the hematopoietic system was well protected. So we selected this dose to evaluate the efficacy of trichostatin A, which is a pan-histone deacetylase inhibitor, a very well-known antioxidant and anti-inflammatory agent. We had administered trichostatin A 1 hour and 24 hours after irradiation, and we performed we evaluated TSA for both the development for acute mitigation of the acute and the delayed effect. So we found that 15 gray, which was the LD50 10 dose trichostatin, when it was given, it mitigated the damaging effect to the radiation and 100% survived till 10 days. So at LD50 tone, we could achieve 100% survival. There was less apoptosis, and the intestine also showed very good proliferation and regeneration based on the regulation of the Wnt signaling and the expression of different intestinal stem cell markers, and there was less malabsorption also when trichostatin was given to the mice. And we were also interested to see the gut composition. It was altered, but there was less inflammation in this group. Using all this inflammatory marker, we could establish that. And when we monitored this 6-month-old mice, so this mice did not develop any radiation-induced changes on 6 months. As you can see, we could not see any abnormal changes in the structure, and we could found almost 12.5% survival till 1 year. And this is the status of the surviving mice. It was as good as the age match control. So we conclude that TSA is able to effectively mitigate the radiation-induced gastrointestinal syndrome and promote long-term survival, and this can be a potential candidate target for both acute and delayed radiation injuries. Thank you.
Well, thank you very much for this interesting presentation. Do we have questions? Okay.
Yes.
If not, then we can move to the next presentation by Yubile Pogayastra.
So there is one question.
So in case of GI syndrome, one of the major problem, one is that histopathological changes you are looking for, but there is some infection also takes place. So maybe whatever radioprotector you are looking for, that have also trying to plan to study that whether
Yes, sir, we have extensively.
that already have done it.
We have extensively studied the alteration in the gut microbiota
Achha, that
and
already.
translocation to the blood, and that only leads to sepsis. So
Okay.
all events were minimized when TSA was given after radiation.
Okay. So have you tried some other food supplement along with your radioprotector? That will be also, see sometime whatever that you have got a classical radioprotector, and especially for GI, you know that if you take some food supplementary materials,
Sir,
that also will help it. So if you do try to combine this both, it will be really going to be useful.
Sir, since we are now testing it in small animal, so supporting therapy is not recommended for small animals. So for this, we have completely avoided any supporting care. But maybe when we move to NHPs, we will definitely include the supporting care in our study.
Okay, good work. Thank you.
Thank you, sir.
Well, thank you. And now, Yubile, come on the stage.
Good evening, everyone. Thank you, Chair. Thank you, organizers, for the opportunity. I am just talking about a new approach of high-throughput radiation biodosimetry that is based on RBC membrane-associated protein. This is a new approach, and I'm just moving very first, looking to the timeline. So, as Dr. Shuchi mentioned, the necessity of the urgent triage in case of a radiation and nuclear emergency, we need to segregate those people who are exposed from those who are not exposed. At the same time, we need to segregate those people who are less exposed to those who are more exposed. This is very important, right? So, if we as my talk is all about development of radiation protein biomarker, I would like to bring your attention to the point that it's just 20 years of proteomics that before it entered into radiation biology for radiation biomarker development. And this is a image of the 2D image when first time it was Topio who took over this work. So if you see the development of proteomic technologies, it started somewhere in 1970, and it was very late before it made an entry into radiation biology. But keeping a time pace, what we did, our radiation biologists, they took over very first, and starting with 2005 with the basic 2D technologies, and they have moved very first, and very recently what we have done, we are into the DIA, data independent acquisition, MS, label free quantification, and also to timsTOF where the 4D omics, proteomics is coming into action. So if you look into the hunt for radiation protein biomarker, as of now, most of the proteins, they are single protein biomarker, and it's very difficult, you know, to depend on a single protein biomarker that will predict all the doses and time post irradiation accurately. So definitely a panel will be more suitable. I think all of us will come to the same platform on this. And at the same time, the radiation search of radiation protein biomarker, so far it was all around plasma and serum. So it is very challenging because of the abundant protein to look for the very important low abundant protein. This get eliminated while depletion. So if you see at INMAS, we started from 2019 and a new approach where we targeted RBC membrane associated protein for biomarker development. Already I'm showing in the literature here, there are reports where in presence of radiation, RBC was going to be affected, but nobody so far targeted the development of biomarker that is around RBC membrane. And if you remember Bio 300, how the stalwart in the field, Dr. B.K. Singh, he showed that it is the RBC factors that improved and thus animals survived. At the same time, yesterday, I think Dr. Amit from Beards, he also showed how RBC aggregation happened in presence of thorium. So somewhere the deformability and membrane properties is playing a big role. So this is how our approach, if I see, this is what we did in the proteomic biomarker development. We started with gel-based, we moved very first in collaboration with IIT Bombay. We are moving for LFQ-based approach, and we have moved to 4D omics-based approach using timsTOF. So this is the first panel that we developed from rabbit, and these are the 7 protein panel showing there are these proteins. I can just tell you at certain points, this protein showed upregulation up to 8-fold. And this was published last year. Same way, we developed one second panel, getting the encouragement, some signatures from rabbit, we moved for rat, and we developed another 8 panel proteins from rat that are, here we studied different radiation doses, 2 gray, 5 gray, and 7.5 gray, and this is the panel. And just because of the scarcity of time, I'll just tell you, these are the, what we did so far on the 2D based studies, but we are right now, I am not showing over here, but we are already working on LFQ based proteomics, and we are also doing the validation using the targeted proteomic validation of SRM and PRM. So if you see, this is how the progress for the development of radiation proteomic biomarker happens. It is 2 phases, one is discovery phase or one is validation phase. Mostly validation we have used so far is the Western blot validation, but now right now we are going for the advanced technologies where we are using multiple reaction monitoring and parallel reaction monitoring, where we are guiding the LC-MS machine to detect a particular M/J ratio of the protein that was already identified in the discovery phase. So our purpose finally is the development of a point of care device, maybe if it is not a kit, at least something that a panel based on this panel of protein that can be applicable in case of a radiation and nuclear emergency, so that in it is a preparedness of the country that can be supported in that way. So I would just conclude saying that definitely I understand the omics field that is taken over for the biomarker development in radiation biology. Independently proteomics cannot do, it is all of us should join hand, and you see inclusion of artificial intelligence and advanced computational and data mining will be playing a very important role, and that you know the artificial intelligence called Orange also taking place. Orange, there is a software called Orange that is coming up, and we will be using that also for our panel of biomarker development. So in the conclusion, I would just like to tell you that this is the beginning of the new approach of biomarker discovery, protein biomarker discovery, that is targeted around RBC membrane proteins, and this is the first initiative taken from INMAS, and I will just like to further validation and further studies are definitely required. We are doing it, and this is the acknowledgement slide where I would like to acknowledge my the guidance, the conceptualization that this concept particular was given by my director, Sir Dr. Shudi Channa sir, and this is my team, and I am thankful for DRDO for the funding, and thank you all for patient hearing. Thank you so much.
Well, that was a very nice presentation. Thank you very much. We need to move to the next presentation.
Thank you.
So it's by Pracht Bishti. Okay, then the final presentation will be by Shem Jugjal.
Good evening everyone. I am Ishan from Laboratory of Electro-Optic Systems, LEOS ISRO from Bangalore. So today I'll be talking about these real-time radiation dosimeters that are being developed at LEOS. So the main reason for these is because of the upcoming Gaganyaan missions. We want to develop real-time radiation monitor instruments for the astronauts on board. So one major reason because outside the atmosphere, the radiation environment available, that is quite harsh and different to what is there on the Earth's surface. The major radiation sources are from SPEs and CMEs from the sun and GCRs, along with the constant background of high energy photons and UV from the sun. Okay, so here we have the first step to this, we have developed a UV dosimeter that can provide a real-time measurement, and this is based on silicon carbide detectors that are developed in-house. Right, so we are measuring 3 bands in the UV, and so that is UVC, and part of UVC, UVB and UVA, and the remaining irradiance can be extrapolated by the measurements. So the mission, the orbital parameters for the current mission are quite similar to that of Gaganyaan, so this will prove to be a very useful sort of preliminary test and calibration setup for the actual missions. So this is how the typical data will look like, and as the satellite moves from sunlit to the earth shadowed region, you'll get these sort of on and off periods. So here the irradiance is measured for UV A, B and C as the bands defined in the previous slide are like 4.85, 2.44 and 0.07 milliwatts per centimeter square. Right? So why UV? So UV is classified as a well-established human carcinogen due to its mutagenic and non-specific damaging properties. That is mainly through formation of cyclobutane pyrimidine dimers and 6,4 photoproducts, or is a direct DNA damage by single-strand breaks, or through non-specific damage through reactive oxygen species. So the dose-effect relationship is quite pronounced here, so with the individual response varying with the skin type and degree of myelination. So the International Commission of Non-Ionizing Radiation Protection has endorsed a limit of 3 millijoules per centimeter square as a critical limit, and that is for the weighted irradiance. So even for a very low dosage of 3.3 microwatts, it can cross within 15 minutes. So life on Earth has largely adapted to the presence of UV, but that is only starting from 300 to 400 nanometers. As I told, the remaining bit of UV is completely attenuated by the atmosphere. Okay, so here in the purple you have the relative damage coefficient that you can see can peaks at around 260 nanometers, and that is well outside the wavelengths available on ground. So the global UV solar index offers a unitless parameter that can quantify the level of biologically effective irradiance present. And so that is defined for ground starting from 300 to 400, and we have extended the same scheme to starting from 200 to 400 to monitor the biologically effective irradiance that the astronauts are experiencing. So here are the measurements, and with this, if we compute the critical time required, the time required to reach the critical dosage, it comes out to around 3.2 seconds, and the effective dosage is around 1 milliwatts per centimeter square. Okay, So with these inputs, we can sort of use these to design the viewports that will be responsible for letting whatever optical light through in the viewport, and this will be the irradiance that will be incident on the astronauts. So here, if we sort of take these as inputs, we can say that if the viewports have an optical density of 5.43, that should provide enough attenuation for a 10-day mission in a LEO orbit. And so apart from that, if we look at the differences in the irradiance values on ground and on the surface of the Earth and top of atmosphere, it is almost around 40 times. So this also highlights the sort of reason for which this shielding or effective shielding is required, and the effective shielding provided by the atmosphere to support life on Earth. So also on LEOs, we are also developing these dosimeters for ionizing radiation, and we have tested it for its response to alpha particles. And these are again real-time dosimeters which can give an alarm for sort of any high dose scenarios, and so critical action can be taken during the mission. So okay, that's all.
Okay, well, thank you very much. Interesting presentation. And because you are good in time, we are going to allow one question.
Yeah.
Yeah.
Very good work from ISRO. And so when you are looking for UV, so what level of you go for different space? Do you go to deep space also, or it is what type of data you got it?
So the UV levels is more or less the same throughout the Earth orbit, like whatever orbit you go for. So it depends on the Sun-Earth distance.
Okay.
So as you move away from the Sun, the UV levels will drop as 1 by r squared.
So okay, it drops also.
Sorry.
Since UV exposure is one of the major problem for the space. So
UV exposure and the higher energy radiation. So
yeah.
both are quite a problem, and but addressing UV is quite a bit easier.
Okay. Yeah, since you can shield by easily.
Yeah.
Yeah. But it is a good work.
Thank you.
Nice.
Okay, then I'm going to thank all the speakers for their nice presentations, and I would like them to close the session and let you know that there is a business meeting now for the SRR coming up, and then a cultural program. So, hang on.
Thank you, Professor, for sharing the session, and thank you, participants. With this, we now conclude the academic sessions for the day. The next item on the agenda is the general body meeting for the SRR. Members of the society are kindly requested to stay back in the hall, while the non-member delegates may proceed for high tea. The members can join the high tea after GBM. And following the GBM, we invite everyone to join us for the cultural program, which will be followed by dinner. We look forward to your participation and wish you a pleasant evening ahead. Thank you.
An important announcement, we are just going to have the general body meeting. That will be of hardly 20-25 minutes. And then after that, high tea is there. After taking the high tea, a very, interesting this cultural program is going to be held. That is for 1 hour. And after that, you can take meal, and then you can go to the hotel. For tomorrow, I think whenever, because 12 noon is the checkout time. So whenever you leave the hotel, you keep your luggage in the clock room. So once we take the food over here, lunch, then we can go to the hotel. And anytime if you want to go, then everybody will be sent to either airport or other places, wherever they want. So tomorrow, everyone should come. If the family is there, they can stay there for up to 12 noon. So at 12 noon after, they will not allow. And if somebody has booked for further 1 day or 2 days, they can stay there, and they have to pay for their own pocket. Any query, anything, you can ask, you can give me a phone number. Thank you. So I think we're going to start the GB meeting. Anybody who is interested, they can be here, and anybody who want to go, they can go outside for the high tea.